Hey everybody, how we doing? Say hi to Dave, say hi to Rick, say hi to John Messenbrink. How we all doing, people? We're gonna get started in what appears to be 3 minutes. 3 minutes, so be ready. And see if you can guess what the theme is tonight.
It go after dark?
Well, yes.
Looks like John froze up there. Nope, there he is.
Uh-oh.
No, I'm right here.
Something
I'm
on your
still
end.
fluid.
Something on your end's going fuzzy though.
On my end?
Yep.
Just
I see me nice and crystal clear. But then again, it's my computer, so why wouldn't I?
Now something went grainy on you and you're still all blurry. Now you're right. Whatever you just did, just fixed it. Hey.
It was time. I didn't do a thing.
Okay.
You got Jason Mangos on the line. Hey, Jason, look at that.
Jason.
Antonio Marte, how we doing? Andrew McGee, Anthony Rykow has figured it out. Yes, of course. And Rui Silvestri, how you doing, Rui? Welcome.
Wonder how Anthony's day has gone today.
How Anthony's day? Well, if Anthony is listening to the voices in his head, because I know those voices talk to him, it's probably gone well.
he just as long as he doesn't listen to the other voices.
Yes, yes. Wheels is
Wheels
with
is
us
here. Yes.
Yes, Anthony, I hope so. You're right. I hope you're right.
Oh my goodness.
We're not going to talk about that. Okay.
It's not a scarf.
Right. And we have Chris from Ottawa. How you doing? Welcome, welcome. And let's see, several naps, I'm sure. How you doing? Very good. All right.
Mr. Finelli. Everybody got their cocktails.
Yes, everybody have a nice adult beverage. Mr. McGrath, it's good to see you. And Mr. Whelan, where's my boom mic? There's my boom mic right there. I hope you can see that. It's right here. All right.
Mr. Mayo, you got your Mayo Rita tonight?
I do indeed.
Excellent, excellent.
Mayo Rita. Anybody have any Corona? Asked Tom Jones. Oh, come on, that's not your real name. It's not unusual to be loved like by anyone, right?
That is Tom Jones. He's our
That is
rep.
Tom Jones, yes.
That is, yeah, Southwest Sales Reps.
Oh, there you go. What's new,
Vegas.
Pussycat? Whoa, whoa, whoa.
Yeah, I'm sure that's the first time he's heard that.
At least, yes. All right, Anthony, that's 2 for you. You get 1 more and you're out. Okay, hey, welcome everybody to part 4 of Takeo After Dark. Welcome. I'm glad you're with us, and we'll get the screen up there. I'm glad you're here, and hope you guys can see all of us here, and we're seeing you as well. Rick's wearing his nice. Is that a yellow or green Takeo t-shirt?
That's Day Glow Yellow, man.
That's Day Glow Yellow. Very good.
Out near the road, you know, these are handouts on Dave. I got it back at one of your training classes, I guess.
Oh boy, I guess I never got a Day Glow t-shirt.
I know.
Mr. Holdorf, being the classy one of the bunch, is still in his ascot with his whiskey and water. They're very nice, very nice. Or is that
Scotch?
It's Scotch. Well, okay, you got some Scotch, classy guy. All right. And I have gone Caddyshack tonight. I've got my Property of Bushwood Country Club shirt and my Bushwood Country Club caddy hat. So we're all ready to go. We are all ready to go. And tonight we're going to be talking about a lot of cool stuff. And again, before we get started, I just want to make sure everybody knows how this works. We're going to be talking away. We'll have our presentation, which I'm hopeful everybody can see right now. That'll be up and you follow along. Take notes, guys. Pretend you're in a classroom with us and take notes. Write stuff down. So we can all, you'll have a record of it and it helps you keep from like losing focus and stuff like that. So just pretend we're in class together. You'll get the most out of this. If you have a question, you can type it into the question section, that little question mark with a little question mark and a cartoon balloon. That's kind of how you do that. So type that in, and we'll follow along. I think you guys can both see them, so we'll follow along. And ask every couple of 3 slides. Maybe we'll take a question break, and then as we did last week, we'll stay on, guys, as long as you want to, and as long as you have questions, we'll hang out till we're done. If that's till 9 o'clock Eastern, 2 hours, doesn't matter. We got nothing else to do, and pretty much nobody else does either right now. So we will be on as long as possible. And in questions, you've got 2 of the smartest hydronics guys I know looking at you, as well as the guy in red. Okay. I got to tell you, I feel like a giant blood clot in this thing. I just got it today, so I'm not sure if this is going to stay part of the wardrobe or not. But Dave and Rick, I don't know of anybody who knows more about hydronics than these 2 guys. And these 2 guys put together gets kind of scary how smart they are. So any and all questions, please feel free to ask at any point during the presentation. Real quick, I just want to make sure everybody knows how to use the questions thing. If you could just type in a hi, hello, how are you into the question thing. That way I know the 145 or so people out there and however many else log in know how to do that. Okay, and you can hear us. That's the most important thing. Very good, very good. Hey, working well. That's all working
Awesome.
well.
Yep.
Excellent. So, with that said, let's get this party started. On to part 4 of Takeo After Dark. And part 4, the first 3 parts, we've been pretty busy. All right, the first 3 parts we've been pretty busy. Tonight we're going to talk about flow and head loss, how to find the flow, how to find the head, and then how to apply that and really get into the finer points of circulator selection. Even in a residential end, your choice of circulator is really kind of important. I want you to think about that. You can throw in something that'll quote unquote work, meaning people will get heat and they're not going to freeze to death and blame you. That's not that hard to do, but it's very convenient. You can say, hey, it works, what the hell? We have a tremendous overpumping problem in residential hydronics. I mean, a chronic overpumping problem in residential hydronics that we're really not paying attention to. Even with the so-called variable speed circulators, we're really not paying attention to the finer points of circulator selection, and we are still in an overpumping mode. It's not quite as bad, but it's still there. Overpumping comes at a cost, ladies and gentlemen. Somebody's paying for that. All right, and there's a cost associated with overpumping, and it's probably not what you think it is. So we're going to talk about all that tonight. Tonight's going to be a math night too. So you won't have to do it, but just understand that there's math there. And we'll discuss all of that. Where did we leave off last week? I just want to do a quick recap. We left you with a little bit of a discussion of pumping away and what the benefit of pumping away was, and how having the pump on the return side, if you have the right pump, it's not wrong, man. It's not wrong. Systems worked for generations with the pump on the return. So how is it wrong to put the pump on the return? It's wrong to put a high head pump on the return. I will tell you that. A low head flat curve pump generally works pretty well, like what was on most of the older systems, a B&G 100. So we talked about that and got into that discussion a little bit. We did discuss the point of no pressure change, the point where the expansion tank connects to the system. It's the one point in the system where the circulator can't change the pressure. We talked about air control, different air control devices, why it's important, why they go on the supply side, because that's where the water's hottest, and how they work. And we talked about the universal hydronics formula. Now, there's that one math formula you do need to know stone dead cold, man. GPM equals BTUH divided by delta T times 500. That's how you figure out the flow rate. All right, with 100% water. The 500 will change, obviously, with glycol, but that's how you find the flow rate you need to deliver the BTUs required. All right, and then we started off the whole session with a discussion of pipe sizing guidelines based on flow. Once you know the flow rate, how do you size the pipe? Okay, and it's based upon gallons per minute, so 2 to 4 GPM, 3/4, 4 to 9 1-inch, etc. All righty, so that's all part of what we were discussing last week. And now let's get on to the business at hand, and that's circulator selection. And we're going to talk about flat curves, steep curves, 3 curves, right curves, and even variable curves. And if you'll notice, here's a little pop quiz for you. Who's that little dude in the middle up there, that little orange and yellow dude? Who's he and what's his significance to hydronics? Well, I'm going to tell you, this one came from this one. No, it's not Rick Mayo, Steve Whelan. It's not Rick Mayo.
Thanks, Steve.
Okay, we're getting this night off to a good start, are we not? No, that guy is the Lorax from Dr. Seuss. He's the Lorax, and the Lorax. This little nugget of wisdom was given to me by one of my favorite people, James Jeffrey. Call me JJ House, one of the smartest hydronics guys in all of Canada. And he would start some of his programs with this quote, and it always struck me because it's a really good quote to start a program off with. And it's from the Lorax. Unless someone like you cares a whole awful lot, nothing is going to get better. It's not. And I think you can apply that to hydronics. I think you have to pay attention to this stuff. It is, as we've said before, putting together a hydronic system, you know, making the water go round and round, putting in a boiler, wiring it up, piping it, having it make the water get hot. That's not that hard to do. A reasonably competent handyman could pull that off probably for a lot less money than you can. What is it that separates you from him? It's that caring a whole awful lot. It's knowing that, yeah, you know what, this circulator, I take that 3-speed circulator, I set it to high, it'll work, but it's not the right thing to do. All right, it may cause me more problems than it solves. It may cause my customer problems. It may cost my customer money, even though it's easy for me. Understanding that and making a difference in that respect, and making it your job to know what that overpumping thing is and how it happens and why it happens, and taking steps to cure it, then things are going to get a whole lot better. I mean, that's what professionals do. That's what professionals do. And geez, Rick, this is that resemblance is kind of uncanny. I got to tell you.
Just have to grow my mustache out.
There you go. There you go. Maybe that's going to be your new nickname, the Lorax.
Thanks, Steve.
All right. Let's get that. Then you can thank Whelan for that. There you go. All righty. Let's get into this. First off, when we're talking about circulators, we call them pumps for shorthand. Technically, it's not a pump. All right. Technically, it's not a pump. It is a circulator. Pumps pump, circulators circulate. It's a little bit different. All right. Pumps move water from the well up into a tank. Circulators just make water go round and round. It's kind of easy. All right. More technically correct, I think we should call this thing a pressure differential machine. Its job is to create a pressure differential within the system, and then Mother Nature takes over because high pressure goes to low pressure. That's kind of how it works. So it's really a pressure differential machine. Now the trick is to get a circulator that can create enough of a pressure differential to give you enough flow under design conditions. That's when you need the most, right? So sizing a circulator for design conditions tends to be the target. All right, that is the target, and we'll discuss how that's done. All right. This is just a little primer on how the water moves. Okay, how does this circulator work? What does it do? And how does it make water move? All right, inside every circulator is this thing called an impeller. Now, this is an artist's rendition of a closed veined impeller. And this is that's a picture of a 007 impeller, standard efficiency 007 impeller. The 007 impeller is what we call an open veined impeller. The other one is a closed veined impeller. They have different purposes. They do different things and have different jobs. All right, but they all kind of work the same way. All right, they all work the same way. Water will enter the circulator through the eye. It comes in the inlet side of the circulator, and that impeller's spinnerating, okay? And the water enters through the eye of that impeller. And then the veins in the impeller will fling or slap the water from the inside out. So the water's coming in, and the impeller just goes, it just.
Can you?
Are you reading some questions there, Eric?
No.
The water, no.
No, you froze up on my end. So.
Oh, okay. It's just flinging the water from the inside out in a 360-degree pattern. And while it's doing that, it's adding velocity to the fluid. And the discharge side, which is a much narrower outlet than is the inlet, it turns that velocity into pressure. So what comes into the circulator goes out at a higher pressure. Now, some things to understand about impellers that make the applications different. The thicker the impeller, okay, the thicker the impeller, the more gallons per minute a circulator can move at a given RPM. So the thicker the impeller, there's more room for water in there, okay? It can move more gallons per minute. The larger the diameter, okay, the larger the diameter, how big across it is, the longer the fling for that water, right? The larger the diameter, the more head pressure differential the circulator can create, okay? So the bigger around that impeller is, it becomes a higher head pump, all right? A higher head pump. And then if you increase the speed of any impeller, you're going to get more flow and more head pressure differential. It's going to just give you more of whatever the heck it was doing. So a 3-speed circulator, okay, you know, whether it's a Takeo 0015, a Grundfos 1558, doesn't matter, is going to have 3 curves like that. So low speed, medium speed, high speed. It's the same basic pump curve. It looks exactly the same. It's just a little more of whatever it was. All right, when you make it go a little bit faster, it gives you more flow and more head. We move that thing up. It doesn't change the shape of the curve. It doesn't turn a steep curve pump into a flat curve pump and then back into a steep curve pump. It can't do that. All right, so the pump curves stay the same. So the thicker the impeller, the more flow, the larger the diameter, the more head pressure. Now we have different kinds of circulators. We have what we call steep curve circulators, and we have what we call flat curve circulators, and they're a little bit different. We're going to get to those in a second. We have any questions out there, guys, that have popped up? Anything that you think we need to address at this point?
At this moment, nothing now.
All right.
I'm keeping an eye on it, so we're all good to go.
Excellent. And again, folks out there, just when you get a question, when it pops into your head, just feel free to type it in, and we'll address them as they come. And speaking of which, let's talk about what this thing we call head pressure differential. Head is a term for expressing pressure in hydronics. Now, the piping is creating the pressure loss or the friction loss, and that circulator needs to overcome that friction loss. That's what we size it for, okay? And we use feet of head, and it's an unfortunate term because people think feet of head, feet of height, and that's not how it works. The reason we call it feet of head is basically 1 PSI, all right, is equal to 2.31 feet of head. That comes from something we talked about last week, or the week 2 rather. A column of water 2.31 feet high will have a gauge pressure at the bottom of 1 PSI. All right, so 1 PSI of pressure loss through the piping system is equal to 2.31 feet of head loss. That's kind of how that works. All right. Now, there's 3 different kinds of head that we're talking about in hydronics. There's static head, and that's your system fill pressure. That's typically up to 12 PSI. Now, there's friction head. That's what happens in the piping system. We have to overcome the friction head or the head loss. Our circulator has to overcome that head loss. And then we have pump head, and that's the pressure differential the pump can create. All right, that's what the pump is capable of doing. So just so you understand, there's 3 different kinds. Now, again, that feet of head thing is kind of unfortunate because people, when they think feet of head, they think feet of height, and they think, well, I need a high head pump to pump up to that 3rd floor or 4th floor or something like that. I need that high head pump. The important truth is the physical height above the heating system, or the physical height of the heating system above the boiler has no relationship whatsoever to the head pressure of the pump in feet. All right, the 2 are completely irrespective of one another. The circulator does not have to lift the water up 3 flights of stairs, all right, to radiation way upstairs. The system's already filled and pressurized. We took care of that with the static head, all right? That's already been taken care of. So the circulator doesn't have to pump the water up there. It's already filled. All right. Now, some people say, well, wait a minute. What about the weight of the water? Don't I have to push the weight of the water up? Well, no, because you got the same amount of water coming back down the other side of the closed loop system to act as a counterbalance. Maybe the better way of looking at it, folks, is to think of it as a Ferris wheel. All right. If I'm sitting right here on the Ferris wheel, right, does the motor on the Ferris wheel have to lift me up? No, because Dave's over here and he's kind of counterbalancing me. All right. And we'll have Rick up here, all right? And Wheels will be down here, and Messenbrink's over here, and the rest of the crew, you're all over the place, all right? So, the Ferris wheel doesn't have to lift me up because there's another guy in this cart over here acting as a counterbalance. Really, all the motor on the Ferris wheel has to do is overcome the friction loss of the bearing assembly right there. All right. Another way of thinking about the water and a pump in a hydronic system is to think of the water as a bicycle chain and the pump as the pedal. When you start pedaling, every link in that chain moves at exactly the same time and at exactly the same speed. All right. Whether, so there's no pumping up or, worried about the height or anything. It's already filled. It's already pressurized. The water just has to go round and round. So that's why a circulator can do an awful lot of work at very, very low horsepower. Typical 007 standard efficiency is a 125th horsepower motor. All right. That's a little itty bitty pump, but that moves a hell of a lot of water. It can move up to, well over 25 gallons a minute if you need it to. So understand that because of that, circulators don't need to be really powerful. All right. For residential applications. Let's go through a quick just run down of some TACO circulators, just so you know what they are. We have an awful lot of standard efficiency circulators with an awful lot of numbers. I want you to think of these as different families. The first are the little guys. Okay, these are the wee folk in the family. The 003 and the 006. They're little pumps, low flow, low head, little pumps, used primarily for domestic hot water recirculation. There may be an instance if you're doing variable speed injection mixing, if anybody does that, where a 003 or a 006 would be just fine. But in most cases, these are domestic hot water recirculation pumps. Then you have the flat curve family, the 005, the 007, 0010, and 0012. They're comparison with other circulators. The 007 to this day, folks, remains the #1 selling wet rotor in North America, and it ain't by a little. This thing TACO's been selling this since the mid to late 70s. And yes, to answer your question, the name did come from James Bond. The product manager who was in charge of this project was a huge James Bond fan, and he made that the project name, and it just stuck. So that's why we have the 007. But there are a lot of wide applications for flat curve pumps. Zone valves and flat curve pumps go together like cake and ice cream, folks. That's the perfect marriage of a pump and a zone valve. Steep curve pumps and zone valves go together like ice cream and tuna fish, not really well together. And we'll talk about that. But these are your flat curve families. And the reason we call them flat curves is you have to compare them to the steep curve family. The 008, the 0011, the 0013. These are lower flow, higher head, steeper curve circulators. Where might you use these? Well, radiant tends to live right in here. So these are used a lot with radiant applications. Heat exchangers, sometimes they're used as boiler circulators for ModCon boilers that have high head loss heat exchangers. They can be used for indirects that need high flow rates, snow melting, those types of applications. Are very common for the larger of the steep curve pumps. And then you have the specialty circulators, the redheaded stepchildren. They don't really fall into any particular category. They're kind of the 009 is super steep, the 0014 sort of kind of steep. They both have very good uses, but they're kind of in the middle. They don't really fit on any of the other charts. And then the 3-speed family, the 0015 standard efficiency 3-speed circulator, very common pump curves to other 3-speed circulators on the market, whether it's the Aquamotion, whether it's the Grundfos, whether it's the B&G or any of the others out there. They're all basically the same in terms of pump performance curves, are very, very similar. That 0010 is kind of an interesting one. It's a flat curve 3-speed pump. That's designed to be a service pump. We use the 0010 3-speed for guys who service those older systems that have the B&G 100 on the return side. You'll remember the last time we talked about that. That's a flat curve pump, very low head. In what the 0010 is designed to do is designed to be a easy swap out for that pump when that pump finally dies, that won't change the dynamics of the system. And the flap on the box actually has a cross-reference chart. If you have this pump with this motor, set it to low, this pump, this motor, set it to medium, that kind of thing. So that's why we have the 0010 3-speed. All right. And into variable speed, here's our simple basic ECM variable speed pump, the 007E. No settings, it's one pump performance curve. All right, from here to here, it's a variable speed pump. From here to here, it's a fixed speed pump, just like anything else, but there's no selections to be made here. It's a very simple, very straightforward. If you like 007s, you want to go high efficiency, put in a 0070, you'll get virtually identical performance with some variable speed capabilities, and it'll be a little bit more electrically efficient. The 0015E3 is designed for people who like 3-speed circulators. This is a 3-setting circulator because we have variable speed here and we have variable speed here. The high setting is full speed, fixed speed, all right, contractor no callback mode, but both the low and the medium settings are variable speed. And if you look at them, they're kind of the ultimate flat curve pump, which makes it perfect for zone valve applications. And you can use this for zone pumping too, as we will see. All righty. We're about halfway through here, and I wanted to throw this at you. Remember, we had a trivia question last week. Well, we're going to do it again. Do we have any questions out there before we get into this that we need to address, Dave and Rick?
We have had a couple of questions come in the last couple of minutes.
All righty.
And one of them is feet per second is very important for heat transfer, Andrew, as well as for wear on system pipes and components. How do we find the feet per second in a pipe based on GPM and pump curves?
Ah, very good, very good. Well, feet per second, mathematically, Rick, do you have some math at your fingertips for that? I mean, it's really not a fingertip math thing.
No, I'll send him. I think I can respond to that question directly, and I'll send him the calculation. So if we know what the inside diameter of the pipe is, okay, we can do that calculation and figure out what the feet per second is. So
right. What you're looking at, though, essentially the way to backwards engineer that is we know 2 to 4 gallons per minute and 3/4 inch pipe is kind of where we want to be. We got a little bit of leeway on one side or the other, absolutely, but 2 to 4 gallons per minute and 3/4 inch pipe is going to keep us within that 2 to 4 feet per second set of guidelines for a closed loop hydronic system. If we have 1-inch pipe, we're talking 4 to 9 gallons a minute, 1-inch copper. That also stays within the 2 to 4 feet per second guideline. 9 to 14, 1 inch and a quarter, 2 to 4 feet per second. 14 to 22, 1.5 inches is 2 to 4 feet per second. Now, when you're looking at a pump curve, we'll discuss this. We'll know if we might be starting to push that a little bit, but there's math to know how far you can push it. And maybe that's something we can discuss, maybe do something on next week. That's a pretty good question. All right, other questions out there? Were there a couple more? Or shall we just...
Actually, most of them were related to that one there. I guess another question was if the scotch that I'm drinking is good because my cheeks are all red. Yes, it is. I am enjoying the scotch. I did a little work outside today too for lunch break, so that got me there too a little bit. So nice day on Long Island. Yeah.
Very good, very good. And who was our winner last week?
Last week was Gary Thompson. That was the other question that popped up. So yeah, Gary Thompson, who is here tonight. Congratulations, buddy. We've got your email address. I don't know if we contacted you just yet, but we will give you an email to get your mailing address, and we'll send out that 0018 to you.
Hot dog, hot dog. All right, tonight's TACO trivia question of the night, and if you know it, type it in. All right, if you work for TACO, you're not eligible. All right, just be fair out there. But if you know the answer, type it in, and you'll have to have the right answer by the time we sign off tonight, and then we'll pick a winner at. Well, TACO started in 1920 back in Elizabeth, New Jersey. We discussed that last week. TACO started in 1920 and in Elizabeth, New Jersey, by the White family, that gentleman in the upper left-hand corner. Today, TACO remains a family-owned, U.S.-based global manufacturer. All right, now run by that gentleman's grandson, Johnny White Jr. Now, the question is, in what 2 New England cities does TACO manufacture products? In what 2 New England cities does TACO manufacture products? All right, type your name in. I know you guys know this. Type your answer in, and we'll pick a winner at random over the weekend to receive a TACO 0015E3 circulator. A TACO 0015E3 circulator, which I think Dave is holding up right now, or he should be anyway. All righty, let us continue. Let's get into sizing. All right, let's do a sizing exercise now. Let's size us a pump. All right. And we're just going to keep it really simple. There's other things out there, but I want to keep it simple just so we understand. We're going to do one zone of fin tube baseboard. One zone of fin tube baseboard. There's under design conditions, we have a 30,000 BTU load. That's the heat load of that zone. So it's a big honking zone, all right? 30,000 BTUs is a big honking zone. And we're going to design around a delta T of 20 degrees. So it's a 20-degree delta T, and we're going to presume 100% water. So our formula, as we learned last week, GPM equals BTUH divided by the product of delta T times 500. So in this case, GPM is going to equal 30,000 BTUs divided by our 20-degree delta T times 500. All right, so 30,000 divided by 20 times 500, if we further simplify, that's going to be 30,000 divided by 10,000. So simple math tells us the required flow rate, all right, is going to be 3 gallons per minute, 3 GPM. So 30,000 BTUs, I need 3 GPM based upon my 20-degree delta T. All right, so far, so good, 3 gallons per minute. Now we have to figure out our head loss. Now there's 2 ways to do this. We can estimate the head loss, which is our Friday afternoon, got to figure out what we need here kind of an approach. And this approach works, but understand this approach will overestimate your head in many cases considerably. It's incredibly safe. It's a safe formula, but it will overestimate your head in most cases, all right, about 95% of the time. All right, but here's the formula, because it's a pretty simple formula that you can keep in your head. All right, the first thing you got to do is measure the run as best you can. Now you can't get up there with a tape measure and measure every inch of pipe unless they give you free rein in the house with a Sawzall, which is a hell of a lot of fun, but I don't think they're going to do that. So what do you got to do, man? You got to estimate. You got to use your experience as a pipe fitter, being in houses under construction as a pro. Okay, if I were running this zone, how would I do this? How long could this zone possibly be? So you go, okay, I got 5 feet up, I got 10 feet over, I got 30 feet that way, I got 20 feet that way, 30 feet coming back, 20 feet over and 10 feet down. Bing, 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 bing. Okay, there's my best estimate, and add a little for safety. I mean, that's really is the best that you can do, but it's also the least you should do. You got to do at least that much. All right. So we want to measure the run. Now we also have to take into account, valves and fittings and stuff that's in the way. We have to account for all of that. Now, again, we can't get in and count them all, so we got to allow for it. And how do we allow for it? We allow for it by multiplying by 1.5. What we're doing is we're measuring the run and then adding 50% of that to allow for valves and fittings and stuff that's in the way that's normal. If there's something really weird in that run, then we got to add that separately, but this should cover you under most conditions. So multiply by 1.5. That gives you something called the total developed or the total equivalent length. Now, once we have that, we're going to multiply it by 0.04. Now, 0.04 represents 4 feet of head loss, 4 feet of head loss for every 100 feet of straight, properly sized pipe at the maximum flow rate for that size of pipe. Let me say that again. 0.04 represents 4 feet of head loss for every 100 feet of straight, properly sized pipe at the maximum flow rate for that size of pipe. So this formula can be used unchanged for every size of pipe. I don't have to change any of the multipliers simply because I'm doing 1 1/4 instead of 3/4, because the pipe sizing guidelines, all right, are all based upon a minimum velocity of 2 feet per second and a maximum of 4 feet per second. So that makes this formula transferable for the most part for every size of pipe. I don't have to change any of the multipliers. So we measure the run, multiply by 1.5, and then multiply by 0.04. Or if you're into that brevity thing, man, measure the run and multiply by 0.06. It's the same thing, it's just one less step, but this way I can explain it. Because if you were to multiply 1.5 times 0.04, you get 0.06, so it's the same thing, only different. Alrighty then, let's continue and let's do one. So here's our example, okay? Let's say we've got the boiler down here somewhere, all right? And we're gonna do a zone that goes up like this, over here. It's gotta go under the slider like so. We go into the bathroom behind here. We'll pick up a piece of heat here. Then we'll go do the bedroom den. Then we drop in. We put something here in the entryway. We go over to the laundry room, put something over here, and into this half bath. And then we're going to come back down here and go back to the boiler. Something along those lines for that particular zone. So let's measure that all out. We come up with a total measured length, including the element in the baseboard, of 135 feet. All right, just taking a number, 135 feet. Next, we're going to multiply that by 105, or 1.5 rather. 135 times 1.5, that's 203 feet. 203 feet times 0.04, that gives us just a shade over 8 feet of head. So our circulator for this big honking 30,000 BTU zone, all right, big honking 30,000 BTU zone, 3 gallons a minute at 8 feet ahead. That's all I need. I don't need any more than that. And I'm only going to need that on the quote unquote coldest day of the year when I need 30,000 BTUs. That's the only time I'm ever going to need that. When it's warmer out, I don't need as much. All right. I mean, in most of the heating season, I'm going to need half that or less. Is a pump curve chart that we have, and I'm still not entirely sure why we have it other than to show you we've got it all. All right, this is a pump curve chart with with a bunch of lines on it representing a bunch of different circulators that we have, fixed speed circulators. So if we look at, say, at 3 GPM here at about 8 feet ahead, right here's where I need to be. Now let me ask you guys, type in your answer. What circulator would you select here off of this chart based on that requirement? What would you select? All right, we got a bunch of them here. We got 007s, we got 005s, we got a 0015, okay. 0034E says Nate. Yeah, sure, we've got to get those out there. Yep. Pretty much everybody's right about the 005. If you look at the, first off, when you want to select a pump, what you're looking for with a performance curve that is either even with or just a slightly above that requirement, that flow and head requirement. Just even with is better. A little bit above is okay. What you want to try to avoid is a lot of white space between your pump performance curve and the requirement. So if we were to apply those principles here, yeah, you know what? The 005 would be the best choice. If you take a look at the 005, it really looks to be the 007's kid brother, right? It's the same curve, just a little bit less, all right? Just a little bit less. Truth be told, the 005 is not a terribly popular circulator. Try finding one, number one, and number two, because of scale, it might be almost twice as much as a 007 to buy. So it would be a better choice, but the 007 would be an acceptable choice as well. Because of something I want to show you here. Now, in addition, I could also choose the 008, which is this guy right here, which is essentially the same as contractor no callback mode on anybody's 3-speed pump, the 1558, our 0015, any standard efficiency 3-speed pump. That's going to be contractor no callback mode, speed 3. But remember what I said about that white space between the requirement and the line. If I pick the 007, there's some white space, but not a lot. If I pick the 0015 or the 008, there's a lot of white space. My next question for you is if I'm going to choose either between the 007 and the 008, where do you think, and just in terms of GPM and head, where do you think the system will actually operate? Because I'll tell you what, it ain't going to operate at 3 at 8. Just not a chance. It's never going to operate at 3 at 8. It's going to operate somewhere on the pump performance curve of the circulator you put in. It has to. It's one of those thermodynamics things. Energy in equals energy out. No matter what circulator you put in on a job, save for one, No matter what circulator you put on a job, the system's going to do what the circulator says. I've heard people say, well, the system's going to do what the system's going to do, which is utter nonsense. The system's going to do what the pump tells it to do, because the pump is making the water move on that line. All right. So the system's going to do what the pump says it's going to do. What I want to ask you guys is, where on the 007 curve do you think the system will work? And where on the 008 curve do you think the system will work? Just in terms of feet of head and in terms of feet of head and flow rate, what's your best guess? Just looking at this thing, where do you think it's going to run? That's what I'd like to hear from you. What flow rate and what feet ahead? All right, let's see what you got.
And John, clarify that you're talking about just that zone calling by itself.
Yeah, just that zone calling by itself, because it's a single zone. It's a zone pump. That's one pump for the one zone.
Okay.
Right? So it's going to have to work somewhere on the 007 curve or somewhere on the 008 curve. Where do you think, in terms of flow and head, is it going to work? All right. Okay, we got a lot of good guesses, a lot of good. Most of you guys are pretty on. The reason I ask you this is because I want to get you prepared for a concept called the system curve. Now, the system curve is interesting. The system curve is a unique fingerprint for every hydronic piping circuit. It's a unique set of flow and head characteristics. And after we're done with the main presentation, I can whip out my system sizer wheel and show you how to plot one out. But a system curve is the mathematical correlation between flow and head. In a piping circuit, as flow increases, head increases exponentially. All right, it's a function of the square of the increase. It's kind of weird, but it increases. It shoots straight up like a rocket ship. All right. So in this example, I'm going to extrapolate out a system curve for 3 gallons a minute at 8 feet ahead. We know let's go back here. We know 3 at 8. We also know in no flow, there's no head, so 0 at 0. We can calculate at 1 gallon a minute, maybe the head loss is here. At 2 gallons a minute, maybe it's here. We know it's here at 3, maybe it's up here at 4, maybe it's up here at 5. And you just connect the dots, all right? You connect the dots like so, all right, more or less. All right, and you can kind of get the idea, right? So what's going to happen here is, when we connect the dots, the system is actually going to work where the system curve intersects the pump curve. It's going to work either here or here. Now, I want 3 at 8, but if I were to use the 007, I might be getting close to 4. Maybe it's 3 3/4, 3.75 GPM, so more or less. Maybe that's where we're at with the 007. And if we go up to the 008, maybe we're at 4.5 GPM instead of 3. Is this a crisis? Is this a problem? First off, let's say in either case, the system's going to work. You're going to deliver the BTUs, because if I can deliver 30,000 BTUs with 3 gallons a minute, I sure as heck can deliver 30,000 BTUs at 4.5 gallons a minute, right? People say, well, you get more flow, you're going to get more heat. Don't need more heat, all right? Don't need more heat. That's not the point. We absolutely don't need more heat, so it doesn't matter that we possibly could, all right? What you have here is something going back to the universal hydronics formula. Now, if you remember the universal hydronics formula, that stated that GPM equals BTUH divided by delta T times 500. Pardon my handwriting. So in this case, I have 30,000 BTUs, but instead of 3 gallons a minute, I'm delivering this with 4.5 gallons a minute if we were to use, let's say, the 008 or your 3-speed pump at high speed. 4.5 gallons a minute times my delta T times 500. Now, we designed around a delta T of 20, but our flow is about 50% more than we actually need it to maintain a 20-degree delta T. So folks, what has to give? What has to give is the delta T. The delta T is not going to be 20. In this case, it might be about 17.5. which again is not a horrible thing. That's really not terrible, all right? But it's not 20. So the best, but here's the thing, guys. The best delta T you're ever going to see here is 17.5 in this case. And that's under design conditions. If you walk in at 50% load, so it's 15,000 BTUs, your delta T is not going to be 17.5. It's going to be like 8.75. All right. And write this down. This is a good number to keep in your hip pocket. We will spend about 50% of the heating season, 50% of the heating season at 1/3 load or less. 1/3 load or less. So that's 10,000 BTUs. I'm still always pumping at 4.5 gallons a minute. That's what it's always going to do. So I'm going to spend a good chunk of my heating season with a delta T of less than 5 degrees. Tell me, friends, what's that going to do to the boiler? All right, you tell me what will happen to the boiler if I'm sending the water coming back is only about 5 degrees, 5 degrees lower, 5 degrees lower than the water going out. Yeah, everybody's writing that in here. Short cycle, short cycle, short cycle, short cycle. Yeah, the circulator's making this happen. The circulator is making this happen, and it's not a horrible. This is not a bad. That's not horrible. This is not horrible. We've been doing systems like this forever. But understand, the more that boiler short cycles, the less overall system efficiency you have, right? Everybody knows that a short cycling boiler is not a terribly efficient boiler. And we're short cycling the boiler a little bit more on the day of the year where it should be short cycling the leastest, all right? That coldest day of the year, it's still going to short cycle, and it's only going to get worse. The circulator, my friends, has more to say. The circulator has more to say about the overall efficiency of the system than we've ever given it credit for. And that's one of the things we have all, as an industry, learned with the advent of the ECM circulators, of variable speed circulators. Okay, so that's given us a door to understanding the value of variable speed circulators. It's not just you press a magic button and it figures everything out for you. That is a fairy tale. That does not exist. All right. And it's not that it always gives you the right flow. No, it just gives us a fighting chance to battle this. All right. And to enhance the efficiency of a system instead of limiting the system efficiency and intentionally limiting the system efficiency. So that's kind of, I just want you to think about that in terms of when we start picking circulators, specifically fixed speed circulators. But I'll tell you what, variable speed circulators don't automatically cure this either. You still got to know what you're doing. They don't automatically cure this. All righty, let's take a look at the same thing with a 0015, a standard 3-speed, okay? So here's 3 gallons a minute at 8 feet ahead. And you know what? Even though the blue line for low is a little bit below that number, I'd be fine running it there. I don't think that's a problem. I'd pick low every day of the week. It's close enough because I know, using the math formula that I used, I'm overestimating the head. So in this case, I know low is fine. Unfortunately, we all know where is this circulator going to get set in most instances. If a guy's not doing the math, he says, boy, this is a big zone. This is 30,000 freaking BTUs, man. That's a long pipe run and a lot of BTUs. I better give this thing all she's got. I'm going to set it to contractor no callback mode, or at least medium. If the guy has commitment issues, maybe he'll put it on medium. But here you see now he's gone from 3 gallons a minute to 5. To 4. He's at 4 gallons a minute. That's 1/3 more flow than he needs under design conditions. The best delta T he's ever going to see is probably going to be about 15. All right. And if he goes contractor no callback mode, I mean, he gives it the full Monty. Now he's up here about 5. All right. And now he's going to have if he gets a delta, if you walk into that house and ever see a delta T in double digits, you'll be lucky. All right. You will be lucky. So, but this is normal. This is what people do. All right. This is what people do when they say, I don't know, just put it on full speed and let's get the hell out of here, house, they're paying more for the system to operate than they need to. And also the other side, the side killer of short cycling is every little piece of moving equipment in the system is going to have a much, much shorter lifespan. How many of you guys have had to replace weird little components in heating systems, maybe before you thought you had to, generally right after the warranty's over, which pisses off your customer, but maybe before you had to, whether it's an igniter, an ignition module, you know, some sort of a relay, some sort of a moving part that cycles itself into an early grave because we've done this level of overpumping, which most people might not think it's extreme. 3, I'm giving it 5. What's the big difference? Whoop-de-doo, everything's happy, everything's working. Nobody's calling me to complain, all right? You know, and the homeowner may not know. The homeowner's never going to go down to the boiler room and say, hey, you promised me a 20-degree delta T. It's only 8. Get your butt out here and fix it now. You know, you're never going to have that conversation. But you might have that conversation is how come all these pieces are wearing out? What's going on here? You know, or my fuel bills, I thought they'd be a little bit lower. What happened here? Are you sure this thing's tuned properly? Those are the conversations that happen. All righty. Any questions out there, guys? Dave and Rick, what do we got?
Somebody was asking him for you to repeat the amount of percentage heating season spent at what?
Oh, okay. Very good question. Statistically speaking, we will spend 50% of an average heating season, 50% of an average heating season at 1/3 load or less. All right, 50% of each heating season on average is spent at about 1/3 load or less. All right, so say you do a heat loss for a house and you come up with 75,000 BTUs for the load. About half the time it's going to be about 25,000 BTUs or less. So that's kind of where that comes from.
Another way of looking at that too is when we look at how long are we at design temperature, and if we use ASHRAE's numbers, ASHRAE says we're about 97.5, so 2.5% of the time are we ever going to be approaching what we sized everything for in the first place. So it goes along with what John's saying, that folks, let me go back just a little bit. I mean, I probably wouldn't have a problem knowing that I would have chose that 006 pump. But as John says, that's probably twice the money as a 007. So people aren't going to do it. I'm reasonably sure that 006 would have done that job.
006
stepping back,
fine.
Yeah, stepping back to a permanent split capacitor motor, the traditional pumps.
And the other thing to consider here is that 50% of the heating season at 1/3 load or less isn't on the calculated heat load that you've done. It's on the actual heat loss of the house. And they're not always the same thing, right? Because sometimes, I mean, we've all walked into a house where there's baseboard everywhere and they got 125,000 BTU boiler and the load might be 60,000. The heat loss might be 60,000. So that thing's going to short cycle like crazy anyway. And we're going to over pump it. So we're putting that short cycling into hyperdrive. Okay. So that's just kind of crazy. But what I just gave you is way too rosy of a scenario, because here's the reality. We overestimated the head. I want to show you how bad it really will be. Okay, because we're going to look at doing head loss the right way. This chart comes from the Copper Development Association's Copper Tube Handbook. Probably about 198 pages of mind-numbingly boring, data and insight into everything you ever wanted to know about copper, but were afraid to ask. The one thing about the book that's useful is table 6. It's the pressure loss of water due to friction in types K, L, and M copper tubing. All right. So let's take a look at what the head loss would really be. All right. And this is going to give us a PSI per linear foot of tube. It's PSI per linear foot of tube. Add into feet ahead because we know the magic formula, right? So let's take a look at this. Look at our job. All right. We're using 3/4 inch pipe. Remember, the flow rate was 3 gallons a minute. So we're going to use 3/4 inch type M copper here. So we follow the two lines to where they intersect, and we find that the PSI pressure loss per foot of pipe is 0.009. 0.009. Now it's time to do a little bit of math. We told you about this earlier. Let's do a little bit of math, all right? The math is going to look kind of funky. Now, this chart, actually, if you go to your handout section, there's a little button on your control panel. There's a hand called for handouts, and what we have there is the takeaway sheet. It's got a lot of different math formulas and stuff in there for you, but it also has this chart. If we were to go and actually count fittings, all right, this is the equivalent feet of pipe for different kinds of fittings. So a 45 from 1/2 inch up to 1.25 inches is worth 1 foot of pipe. A 90 is worth 2.5 feet of pipe. A full port ball valve is worth 1.9, 2.2, et cetera, et cetera. So this chart is in the takeaway sheet. So you can download that now. It's in the handout section. There should be a little button on your thing that if you press it, it'll give you, you'll be able to download that that sheet for yourself. So we just, here we're going to count them up. All right, 2290, some ball valves, pipe. All right, add it to the 135 length. Okay, we're at 200 feet total developed length, just as we were if we multiplied by 1.5. So we're close enough. Now 200 feet of pipe times 0.009 psi worth of pressure loss per foot of pipe. If we multiply that, 200 times 0.009, that gives us a pressure loss of 1.8 psi. To convert that to feet ahead, we multiply by 2.31. So 1.8 psi times 2.31 feet of head per psi, that gives us a touch over 4 feet of head. In reality, remember we estimated, we came up with a touch over 8. We calculated, we come up with a touch over 4. So in this case, we overestimated the head by double. So let's go back here, 3 gallons a minute at 4 feet ahead. Now, you know why I said low was going to be just fine? This is why. Low is going to be just fine. If we calculate out the different intersection spots, again, now look at what happens if we go to contractor no callback mode. Now we're at 6 gallons a minute. Now we've got double the flow. The best delta T we're ever going to see here, boys and girls, is 10, and it's going to get smaller as it gets warmer out. Now we're going to short cycle the bejeepers out of this thing, but no one is ever going to be cold. But do you see what we're doing here? Do you see the problem of the finer points of circulator selection? It's not just covering the dot, man. It's knowing what you're covering the dot with and how much white space you have between your requirement and the pump curve of the circulator that you're using. Always watch that out, watch out for that, and understand the dynamics of a system curve, and the system will always operate where the system curve intersects the pump curve of the circulator you've chosen every single time. For giggles and grins, same length, lower load. Let's try this one, 20,000 BTUs. It's the same length. It's still a 200-foot long zone, with fittings, but there's only 20,000 BTUs. Maybe it's for the other half of the room, or the other half of the first floor, whatever. It's only 20,000 BTUs. It's a lower load by 1/3. In this case, same length, we're at 0.004 psi per foot. If we had simply done the simple way, measured length times 1.5 times 1 times 0.04, we would have come up with 8 feet ahead. But since this is a lower load zone, even though it's the same length, watch what happens. All right, we're going to do some math here. 200 feet times 0.004 psi per foot is 0.8 psi times 2.31 feet ahead per psi. We're less than 2 feet ahead. So now we need a circulator that can do 2 gallons a minute at 2 feet ahead. Remember, this is a 200-foot overall length zone. That's 20,000 BTUs. That's still a big zone, guys. That's still a big zone. We need 2 gallons a minute at 2 feet ahead. Now look where we are. All right. And again, just see what happens. Now if we're at contractor no callback mode, we're 2.5 times what we need in terms of flow. So this is normal. This is what happens when you select a circulator based on convenience rather than thinking it through and really understanding what we're trying to do. Again, in this example, 2 gallons a minute, I used low speed. I'm at 3 gallons a minute. It's not ideal, but it's better than 5. All right, it's better than 5. Alrighty. And one last thing about Pecks. What if we were doing this with Pecks tubing? All right, used your Pecks manufacturer's pressure drop chart. Okay, and you see we've got flow on the left-hand side and the pipe size on the top. So in this example, we have 3 gallons a minute for the zone. And the smallest pipe size we can use here is 5/8 inch Pecks. All right, 5/8 inch Pecks. And if we look at the chart, we find that we have 0.13 feet of head per foot of pipe. This chart gives you feet of head per foot of pipe. So I have 0.13 feet of head per foot of pipe. Now, Remember, that entire loop was 135 feet long. If we're using Pecks, we really shouldn't be using fittings. So we really don't need to multiply by 1.5. Are there fittings, Pecks to copper fittings where we make the connections to the baseboard? And is there pressure loss there? Yes. But I always felt if you consider the length of the element the same as Pecks, you're going to be fine. It's going to cover you. So in this example, we're going to use 0.13 feet of head per foot of pipe times 135 feet. And now we're looking at 17.5 feet of head. So 3 gallons a minute at 17.5 feet of head with 5/8 inch pipe. We can't do that. Not with these pumps. All right. Not with what we're looking at here. So obviously we have too much head going on. How do we reduce that number? How can we reduce that number? Well, we could bump it up to the 3/4 inch Pecks. All right, if we go up a pipe size, we're cutting the head loss in more than half. All right, we could do that. But has anybody here ever, installed 3/4 inch Pecks for baseboard loops twice? You might do it once, but I don't think you're going to do it twice. All right. And if you're struggling with what I'm getting at, has anybody here ever been Peck slapped? All right, where you kind of the pipe over here and you let it go and it smacks you either in the front or the back of the head. That's that's why I am the way I am. I've been Peck slapped one too many times. What you could do is you could use some leftover 1/2 inch Pecks and you could split the zone. It's still one zone, but it's 2 separate loops, equidistant, equal split of the load. All right, so now each half of the load is 1.5 GPM because 30,000 divided by 2 is 15,000 BTUs. That's 1.5 gallon per loop. So we're kind of in the middle here at 1.5 between 0.08 feet ahead per foot, or 8 feet of loss per 0.08 feet of head per foot of pipe and 0.10 feet of head per foot of pipe. I think we could probably agree on a happy medium at 0.09, all right, for our loop. So now we'd multiply 0.09 times about 70 because it's still half the length of the run, right? So half the length of the run times 0.09. Now we're at 6.3 feet ahead, all right? So now we have 2 loops that are in parallel. I don't have to add the head together here. I'm just fine with the way it is. Now I can do 3 gallons a minute at 6 feet ahead with a 2-loop zone, so to speak, and I can use my leftover 1/2 inch Pecks, which can again help drop job costs, use up some scrap, and be able to do this job pretty easily. And that's going to be right about there. Hey, low speed every day. We're off to the races. All righty, very good, very good. Time for our trivia answer. Time for our trivia question answer. I did notice that a lot of people got it right. And yeah, the trivia answer is Cranston, Rhode Island and Fall River, Massachusetts. Cranston, Rhode Island, of course. We've been there since 1950 when we moved into an old, the former Greater Providence streetcar service depot. That's what that building was initially. Fall River, Massachusetts is where we have an ASME rated welding facility. You go there, you see sparks fly. It's really cool. That's where we make our commercial heat exchangers, commercial air separators and buffer tanks and expansion tanks and things like that. That's a fun place to go visit because there's just stuff going everywhere. And Fall River, of course, is also known as the home of the incomparable Ms. Lizzie Borden, who, if you ever meet her, just don't annoy her. That's all I'm going to say. All right. But that's our trivia question answer. Cranston, Rhode Island and Fall River, Massachusetts. Everybody who typed it in prior to me saying so has a chance to win, and we'll put all your names in a hat and we'll pick them out on video like we did the other day. All righty. Couple more housekeeping things before we open it up for questions. Again, you want those Takeo stickers, and Dave, I'm still waiting for my Takeo After Dark stickers. You want some stickers? Contact Takeo Training on Instagram @Takeo Training, and give Dave a mailing address, and he'll send some out to you. And if you have stickers of your own, send them to us. We love to swap. So there's that for you.
Amen. I need some more on the wall behind me.
There you go.
So John, everybody gets theirs first before I send them to you, though. Sorry. Wait a minute. That's not right.
Doesn't being the boss have any privileges whatsoever? Okay, we're done, gang. How about a fresca? I love that line. How about a fresca? Next week, just so you know, for next week, we're going to get into the great zone valve versus circulator debate, and we're going to give you a final definitive answer. The definitive answer, which is better, zone valves or circulators? We will nail that sucker next week on Taco After Dark. So with that, okay, we get questions. We get the webcam back up here. Oop. And let's go. How we doing there, folks? What kind of questions do we have, Dave and Rick?
Well, also minimize your, stop sharing your screen too.
Yep,
So,
I gotta get.
Unless people want to talk about Abbey Road.
Road. Yeah, that's what the best day, one of the best days of my life. I'll tell you what.
You're smiling. I can see that.
Yep. All righty. Excellent.
Marcelo's got a question about the right formula for BTU calculating, which was episode number 1.
Yes, that was in episode number 1. And if you go to Mechanical Hub's YouTube channel and our YouTube channel over the next few days, you can watch this episode 1. And I believe in the Taco After Dark, do we have the Taco takeaway sheet? We do have the formulas there too, just a simple math formula. We don't have all of the other information there, and we can get you that. We have that as a download as well. So if you want to provide us with your email address, Marcelo, we can email that to you. But you can download the simple math formulas right now on the using the handout button. Who's dinglinging?
Oh, that's me. Yeah, I'm just getting notices. Sorry.
Okay, what else do we have here? We got a whole bunch of questions.
Yeah, there was one that came in a little while ago, and I don't want it to slip away. But Jim had asked, would it be correct to say a diverter T system head loss would not be calculated the same 1.5 times 0.04 multiplier? Yeah,
with diverter T's are kind of funny because the diverter T's, if you look back on that chart we had a fairly substantial head loss, and sometimes you use one. In some cases, you have two if the run for the radiator is high. So you've got to do the head loss. You got to calculate the run, not just for the main loop. Whoops, sorry, not just for the main loop. You go through your first diverter T, up through the radiator, back down, along, next diverter T, up, back down, and along, because that's the worst case run there. So yeah, it's a little different. You can't really do 1.5. Maybe 1.75 might do it, but yeah, 1.5 is probably not the right number to use there. At that point, you can count them in many cases and see where you're at. Alrighty, what else do we have?
Somebody was talking about using a type of Pecks aluminum Pecks for baseboard runs, and they like it, and they're singing the praises of it, etc. So I know people have done that, and I happen to be looking at some right now up in my ceiling. So
yeah,
anyway,
there you go. Yeah, there it is. Back to Vega Foster Pecks, and it won't Peck slap you. and if you're bored during lunch break, you can take a small piece and turn it into a hockey stick, roll up some duct tape, and you got something to do during lunch that's kind of fun and active. We found many ways during lunchtime to keep ourselves occupied. I remember one particularly boring RPA trade show where we had a great hockey game going in the aisles because there was nobody there to look at stuff. So. All righty, what else do we have here? Will piping pumps in parallel off of a manifold affect the flow rate and feet of head? In parallel, pumps in parallel will double the potential flow. All right, it will double the potential flow. Pumps in series will double the potential head. All right. So meaning if you go flange to flange with two pumps, it's kind of like a well pump, submersible well pump where they have all those impellers in it, They'll double the potential head that the pumping package can do. Pumps in parallel will double the potential flow that the tandem can do, if that helps.
There's a clarification, or they want us to go over the Pecks piping head loss calculation again. Well, all we did was split the GPM in half and then run it through smaller pipes. The actual numbers we got off are just a printout from Mr. Peck's chart that shows at a certain GPM, you're going to get this much pressure drop in feet ahead per foot. So I'm not sure I'm just trying to clarify the question. So he wants us to go, yeah.
Let me know, does he want us to go back and take a look at that?
It says to go over the Pecks piping head loss calculation again.
Okay, well,
with half inch.
Yeah, what we did was we split the loop in half, split the zone in half, which is a common practice with whether you're using copper or whatever. If it's a really long run, sometimes you just split the loop. And the reason you split the loop is to create, instead of one big long series loop, you have two shorter series loop that are in parallel with one another, but are still on one zone. They're still controlled by the same circulator / thermostat. All right, it's like if you're putting radiant tubing in a big room, and that big room is too big for one loop of pipe, you're doing it in two. All right, it's the same basic idea. What we did with that is we split it in half load wise, which you would be well advised to do. So it was a 30,000 BTU zone. We created two loops of 15,000 BTU each. So that would be 1.5 GPM per loop. And we also strove to make both loops about the same length, which wound up, we proposed it would be about 70 feet for each individual loop. So then we found we had 70 feet, we multiplied it by the pressure loss per foot that we got from the chart, and that gave us the pressure loss for each individual loop. Each individual loop had a pressure loss of 6.3 feet. Now, because they're in parallel, we don't add the 6.3 together, they're separate. The flow we add together, the 1.5 and the 1.5, the circulator still got to do 3 gallons a minute, but it only has to overcome 6.3 feet ahead. We don't have to add them together because they're in parallel as opposed to in series. So let me know if that clarifies it. I know maybe we went over it a little fast, but if that clarifies the thought process, then maybe that will be helpful to you.
Dave, you got one?
Yeah, got one here. It was saying from Chuck. He asked, do you also add boiler pressure drop along with zone valves into the calculation? I guess that would be from our head loss calculations. Yes.
Very good, very good question. And before we do that, I just want to make sure, guys, don't sign off. We're going to stay on as long as you want, but don't sign off, because in just a few minutes, Dave is going to do a pumping away demonstration right behind you. That little rig he has set up is a pumping away demo station, and we're going to run through that in just a few minutes so you can actually see it in action. What happens when you pump towards the point of no pressure change and when you pump away from the point of no pressure change. So make sure you don't leave before you see that. To answer this question, and then we'll go to Dave, provided he's ready, is that in the short answer is yes. Okay, the short answer is yes. The long answer is a little bit different. If it's say a cast iron boiler, all right, if it's a cast iron boiler, think of that cast iron boiler as a big honking open space in the piping, right? The pressure loss through that cast iron boiler is less than the pressure loss through the same length of pipe. I always just consider it a length of pipe and don't worry about it, right? You know, that's just the way it is. Same thing with an air scoop or an air separator. The pressure loss through the air separator is less than the pressure loss through that same length of pipe. So there's no reason to add for that specifically. So, and if we're looking at a modulating condensing boiler that's piped up in a primary secondary manner, we don't have to pump the water. That circulator for the zone isn't going to have to pump the water through the boiler because we have a boiler circulator doing that when it's piped up in primary secondary. So but if it is piped through the boiler, then we would have to under weird set of circumstances. So it kind of depends on how you're piped up. Now for zone valves, if I had a zone valve, if I was sizing one pump and 3 zones with 3 zone valves, what I have to do for that is figure out the head loss through the worst case zone. All I have to do is figure the head loss for the worst case zone. Once I have that down, I don't have to figure out any of the, I don't have to include the others. I don't have to add them together, because it goes back to that parallel piping thing we were talking about with the, where's my other hand? There we go. That parallel piping thing we were talking about with the split zone. All right. If my circulator can overcome the head loss of the worst case zone in a zone valve job, it can overcome all of the others. I don't have to add them together. I have to have the total flow for all 3 zones, because all 3 zones are going to be open at one given point in time. So I have to have the total flow, but the head loss is just for the worst case one. I do not have to add them all together. Real common mistake when people really wind up over pumping zone valve jobs. All righty. How are we doing over there? You ready there, Davey?
Almost.
Is that what Whelan just texted?
I don't know, man, but I like it.
Yep, I got one here
Send
too.
me a
Yep.
copy of that. I'm gonna grow
Oh,
my
yeah.
mustache out again.
Okay, this is
Just
going to
for that.
stick. This is going to stick through retirement, Rick. I'm telling
It
you.
is. Oh,
It's
yes.
a good. It's a Western thing, you know.
There
So.
you go. There you go. All right, the Lorax.
I love it. I love it.
All right, Dave, you want to take over here and walk these guys through it? And again,
Oh,
any
yeah.
questions
Now,
you have,
stop
just,
sharing
fire
your
'em up.
screen, John. So this way you can get this bigger so everybody can see it.
My screen is not sharing.
Oh, it is not? Okay,
Nope.
because
If
I
you
still
want,
see.
if you guys want all Dave, I'll just stop sharing my.
I just turned mine off.
Yeah.
No, I
stop
just
sharing
see.
my
I
webcam.
still see your screen. I still see you working on Abbey Road there.
Yeah. So turn your screen off, and then they can blow Dave's picture way up.
All right. Let's see. Okay, I think I got it now.
Nope.
Nope.
Or it froze. Or
Okay.
there you go. There you
we
go.
go.
Now they can grab the corner of Dave's. I think they can take his screen and hit the enlarge arrows, and it blows it way up. You're still up there, John.
Yeah, I'll get
And
rid.
that's
I'll get
fine.
that here.
That's
There you go. Okay. Nice and
okay.
big. Go get him, Dave.
Muted. Sorry. There we go. I hit the mute button. So I had some free time between yesterday and today, so we built this. Ken Watson, I'll tell you all about it later on. So what we've got going on here, I threw in a 006 E3 circulator. We
Great
have our
pump.
expansion tank in,
Yep.
and I threw an air eliminator up on top, and over here on the side, I got a globe valve. And that globe valve is just being used for, imagine that your heating zone in the system, and I got to put a little load on this rather than just, 20 inches of pipe here. So the two valves that you see, one is going to be if I'm pumping into the expansion tank, and the other is going to be pumping away from the expansion tank. So I only have one open versus the other. And pressure gauges on either side of the circulator. Circulator is pumping to that way, that direction. All right. So at the moment, with this valve open, with the blue valve open, I'm pumping into the expansion tank, and then this is closed off. Okay. And then this is going to my zone around again. Imagine a boiler somewhere over here. So if I were to kick this on, now pay attention to my gauges. All right. Right now, this gauge is reading around 22. This one's reading 21. Yeah, they're a little off. They're a little old.
All the reason to use one gauge.
Yeah. Well, I kind of had a different display and it busted the other day on shipping. So
Dave, I'm just busting your balls. That's okay.
Thank you. So when we kick this thing on, as we talk about pumping into the expansion tank as we did last week, what's going to happen is your expansion tank is being the pressure police here. And that's going to pretty much control the discharge side of the circulator. All right. So as you can see, we didn't really move much on that gauge, but the suction side dropped down. Okay. So now we dropped down to about 18. It was sitting at 22. So the suction side of the circulator dropped off, but the discharge is relatively close to the same as it was before. All right. So if we go and switch it around the other way, all right, I got to turn the power off, switch my valves. So now I'm pumping away from the expansion tank. So this valve is now open. So, and that's closed off. When I kick this on, again, we're at 22 over here. We're at 21 on the suction side. And we kick that on, and our suction side should stay close to what it started off as. And it is. All right. But now what we've got is about 25, 26 discharge. So the pressure differential that we wanted to add to the system is now being done properly in the system. All right. When we start pumping away from the expansion tank.
Nice.
So now this was parts of this came off of a display that Mr. Holohan had given to me a couple of years ago. I had it up at the factory at Taco. And unfortunately, on shipping last week, it had a bunch of PVC pipe on there. It was built for Dan by Amtrol and wanted them to use it. And it sat in his office in Bethpage here on Long Island for so many years that he called me up and said, hey, you use this. I'm not going to be using, and this is when Dan was retiring. So again, thanks to Dan for this. Greatly appreciate it.
Thanks, Dan.
Very good. Now that's about as graphic of an illustration of what we were talking about last week as there is. So that's pretty cool. That's pretty cool. And any questions on that? So does that help you at all? I mean, that's again we still have guys that say that sounds crazy. That doesn't make any sense at all. I need to see it. Well, there you go. There you go. I remember doing a class in Toronto many years ago, and a guy just looked at me when I was explaining this. Guy looked at me like I was insane. I presume it was because I was trying to explain this. It might have been for other reasons, but he said to me, "You're going to have to prove it to me." And I said, "I don't really have to because I didn't make it up." All right. If you either understand it or you don't. If you want to see it in action, we have maybe he's on the show. If he's on the show, you just saw it in action. So there you go. All right. Excellent. These are some more good questions here. Bill D'Agostino, we meant in a zoning application, if you have a 4-zone system and you're using pumps, as they all call, do they affect the flow rate and head? If all 4 pumps are calling, does it affect the flow rate and the head? Well, not through each individual zone, no, but I think through the boiler, what you're going to have is, if you got this zone at 3 gallons a minute, this zone at 3 gallons a minute, and this zone at 3 gallons a minute, well, now you got 9 gallons a minute going through the boiler, all right, and 9 gallons a minute going through your headers and things like that. So if that's what you mean, Bill, then yeah. Again, the head loss through the boiler is going to be less than the head loss through the properly sized header pipe. So again, you can simply consider that pipe, in my opinion, if that's what you are asking. I think if we're there, let me get the camera back up. And how do you like the Bushwood outfit, guys? I mean, this was a big deal for me. Again, I feel like a blood clot. I don't know, man. That's just weird. The bright red. I've never worn anything this bright red or this much bright red.
We're usually not allowed to wear much red at Taco, right?
Right. Unless we're the property of Bushwood. There we go. All right. Where can I see the webinars I missed? Okay. John Messerbrink answered that one. Okay. For Phil. Yep. They're on the Mechanical Hub YouTube channel. They will be on the Taco YouTube channel eventually.
I'm not sure if John has anything to say. Is John's microphone on?
John, chime in, man. He might be sleeping. I don't know. John, did you take a nap?
I'm here.
There he is.
There is a question about CV, which goes right along with pressure drop. And Jim would like to know, can you explain CV ratings relative to pressure drop? ? For instance, what would a heating valve with a CV of 5 equate to pressure drop? Well, Jim, that calculation, if you want to take a note, remember everybody's supposed to be taking notes, is simply take the GPM that you're flowing through that device, right? And divide it by that device's CV. You were saying it was 5, right? Whatever answer that is, you take that and double it. You're going to square it. And then you're going to times that. That gives you an answer in PSI. You take that and times it by 2.31. That'll tell you what your feet ahead equivalency is. So hopefully that answered that question. Dave, you got one?
Sorry, no, I was looking at some other things here. Sorry about that.
John?
Yeah, the definition of CV is the flow rate needed through a piping component in order for that piping component to impart 1 psi of pressure drop on the fluid, or 2.31 feet ahead, right? So if a valve had a CV of 5 and we were pumping 5 gallons a minute through it, the pressure drop would be, altogether now, 2.31 feet ahead, right?
Oh, you were looking for me to answer that?
Well, somebody, one of you two. Yes, I lead these men.
Of course, I'm reading questions too. Sorry.
So if you had 10 gallons a minute going through a valve that had a CV of 5, your pressure drop wouldn't be 2 psi or 4.31 feet of head. It shoots up like a rocket ship. Again, it's exponential, and there's a math formula for figuring it out. But yeah, that's kind of how that works. All right. So it's not kind of the same thing. It just shoots up like a rocket ship. So, for example, in this case, let's see, CV of 2, CV of 5, CV of 2.31. There's CV. Yeah, in this case, well, I'm not going to say I know CV relationships. This is a B&G system sizer wheel, and again, this is there it is. I have the one copy of the original standing right behind me, but this is the one of the greatest tools ever invented for doing these types of math problems. So scale 5 is the CV relationship. Set the known flow opposite the known pressure drop. So my flow is 5 gallons a minute. Okay. The pressure drop is 2.31 feet ahead at 5 gallons a minute. I'm not sure if you can how well you can see that, but I've got that lined up right there. Okay, so it's 2. Well, maybe I don't have that lined up. Yeah, I got it lined up at 6. There we go. So right now I have my CV, that line that says CV, 2.31 feet ahead. All right, is lined up at 5 gallons a minute. Now, you want to find out the head loss, go over to 10 gallons a minute, and you'll find that the head loss through that valve is now 9 feet ahead. Okay, so it went from 2.31 feet ahead to 9 feet ahead. So again, you doubled the flow, but the head went up exponentially. So that would be how you'd use this thing. And someone else had asked about how do you figure the math for a system curve? How do you figure the math for a system curve? Actually, you use scale 5 on the system sizer wheel, and you can download this as an app too. And again, this the competition, but it's the best tool out there. So I'm not worried about giving that to you. So again, up top on scale 5, you see where it says feet ahead, and then in the big white window, that's gallons per minute. That's flow rate. So we had 3 gallons a minute at 4 feet ahead, right? For our zone when we actually figured it out. So you'll see right now I have 3 gallons a minute at 4 feet ahead. Well, now I just read the numbers up at 4 gallons a minute. Right now, that's reading about 7.5 feet ahead, a little less than 7.5 feet ahead. At 5 gallons a minute, I've got about a little over 11 feet ahead. At 6 gallons a minute, I've got 16 feet ahead. Those are the plots on your curve, all right? And you can go the other direction as well if you want to, all right? Again, now at 2 gallons a minute, I'm at less than 2 feet ahead. And way over here at 1 gallon a minute, I'm at about a half a foot ahead. So those are the points on the plot, and you simply plot those on the graph, all right, on that pump curve chart, and then connect the dots, and there's your system curve. And where the system curve intersects the pump curve, voila, we have an operating point. And I've waited so long to say voila. But think about this, guys. Remember back in like 4th grade or 5th grade when you had to do charts and graphs in math? And you do these little math formulas to come out with different points. You put them on the chart and then you connect the dots and you made like a butterfly. And you thought, good God, this is a ridiculous waste of my valuable 5th grade time. I'm never going to use this crap in the real world. This is ridiculous. Guys, today's the day. Today's the day you use that. It actually is a valuable skill that you learned back in school in math. All right, what else we got for questions here, boys?
Oh, there was one up there. Sorry, I dropped it around.
I got one that's related to primary secondary piping, so I'm assuming he's talking about a boiler. And it just says, wondering about primary secondary piping is still having too much flow will short cycle with too big a pump with modulating boilers. So yeah, good point. It depends on the boiler and how its aquastats work and the sensors and everything. But generally speaking, if you're talking primary, secondary, I'll make an assumption that it's a condensing piece of equipment. What we want to do is we want to find out from that boiler manufacturer what their ideal delta T is and use that in the universal hydronic formula for the boiler sizing for the primary boiler pump. The pump that is the primary portion that's going around in a circle. We want to make sure that pump is, you want to sharpen your pencil. You really want to pay attention to that pump if it's going to be a fixed speed circulated, meaning it can be an ECM turned way down or something along those lines, but it's not automatically going up and down on any external signal or anything. We really want to sharpen our pencil. I would generally state, and Steve's on here, he's a boiler guy, there's probably several boiler people on here. I would teach as a general rule on condensing equipment that probably use a start at a 30. Again, check, see what the manufacturer will let you do, but I'm sizing stuff out at 40 all day long on a condensing boiler. So in the universal hydronic formula, I'm using a 40 in the Delta T. Remember, that's design condition. That's a modulating boiler. I mean, I throw this question out years ago when I used to sell boilers, is how often is that boiler going to go to high fire? Guess what? Maybe never. So you're sizing the pump in case it just might go to high fire. You might need to know a little bit more about that, but hopefully that answers. Yes, it's bad to oversize circulators, generally speaking.
No matter where it is. That's right. That's right. I see Jim Hillpiper was the guy that asked the question about the CV ratings. I hope that answered your question, Jim. And please do me a favor, drop me an email. I have a question for you. So just do that offline. If you could just send me an email, I would appreciate it. Very good, very good, very good. Let's see what else we have here. I love these geek sections, but how do you size snowmelt systems? Boy, that's we've all done it, right?
Oh yeah, yep.
You got three guys here who have designed an awful lot of snowmelt in their day.
Well, basically, so generally, what's the question? So
I think you just wanted to know. Yeah, I want to know. We can't answer that one in this forum. Nope. Other than to say, plan for a really big freaking boiler.
Yeah.
Because and make sure we have money to burn.
Yeah. Anywhere between 85 BTUs a square foot to 300 BTUs a square foot. Anywhere in between that for your boiler size. Done.
Right. And it depends on what the homeowner wants. If they want the snow to come falling down, get within about 1.5 feet of the ground and say, oh my God, and try to go back up, then you're talking about you're on the 300 BTU per square foot line. If you just want to, you're going to break out the snowblower or whatever, and you want to get rid of ice and the schmutz that's left afterwards, then you're on the more like the 85 BTU per square foot section. It's all about customer expectations with snowmelt. Absolutely. Okay, what else do we have here? Happy Earth Day. Earth Day's 50 years old today. That's right. I remember the very first Earth Day. I was late to school because I could not understand why the local drugstore wasn't selling candy that day. And I had to have a discussion on, they had to explain to me, which Mr. Garrick, who owned the drugstore, he was a great educator for a lot of kids in town would go to there, and he got to know everybody. And he actually explained why, Earth Day was a thing. So to a 10-year-old kid, or 9-year-old kid at that point, this was like, who knew, So that's one of my memories of Mr. Garrick. Excellent. Okay, great. What else do we have?
All right, I see one here.
Okay.
So Tim Dice had asked, if we have a manifold in parallel, do we add the head loss of the supply and return pipe to the manifold, or we just figure one side?
Oh, return as well for head loss. Yeah, you got to get when you're calculating head loss for a circulator, it's all the way from the Gazauta side of the pump back to the Gazinda side of the pump, because that's how long it has to make the water go. So yeah, it's the whole shooting match. It's from the Gazauta side back to the Gazinda side. So that's your guideline there. Okay.
I'm going to answer Stephen Jansen. He was questioning my 40-degree Delta T, and he's worried about hot spots. Remember, I'm talking about the primary boiler loop in a primary secondary system. I'm not talking about the system side that's going out to whatever type of heat emitters. And I think you're referring to probably radiant floor application. So again, this is a misunderstanding in a lot of world. The boiler can operate at one Delta T and the system can operate at another based on pump sizing. And that's a misconception by a lot of people, even, well, people that should have known better kind of thing. So, hey, we all live and learn. So,
well, he just responded, and he was saying about hot spots on the boiler tubes.
Well, again, the boiler manufacturer will let you know what their minimum flow rate is at a given firing rate. So I'll leave that up to the boiler manufacturer to worry about hot spots on the tube sheet. So a lot of that has to do with water quality. And John, you're going to do that dirty water again? That might be a good segment,
Yeah,
even though everybody's talking about it now.
Right.
But
Bruce Marshall's retired, and he's not as up on the water treatment as he once was. We have another rep actually who's quite good at it. Maybe Patrick S. out there in Minnesota. Maybe he could do that one with us to talk about water treatment and water quality and the importance of that in a hydronic heating system, because that's a big deal. And it's not just using it goes beyond just using one of these things, you know. A Dirt Mag Separator, okay, like this is the Taco's a magnetic dirt separator, okay. So it goes beyond just using one of these. One of these plus water treatment to keep the whole system clean is very important. And I just wanted to show you this because I don't know if anybody have seen this before. It's our 4900 Dirt Mag Separator. It looks an awful lot like an upside down 4900 air separator, which is kind of what it is. But this one has a magnet, all right, a very high Gauss magnet. That's like a very powerful magnet, but this little magnet has a metric crap ton of Gauss. All right, and Gauss is a way of measuring a magnetic field. It's not pull strength; it's a strength of a magnetic field, and this actually has a very powerful magnetic field. Because what it wants to do is, the crappy water goes through this thing, sees these the Paul rings that we have in our system, and it's a collision medium at that point. The crap kind of bumps into that stuff, and the magnet says, "Hey, down here, guys, I got something for you." He tricks it, says, "Come on down, come on down. I got beer and cigarettes. Come on down." And the dirt goes down for the beer and cigarettes, and it can't get out, right? What's that song by the Eagles? You can check out anytime you like, but you can never leave, man. They got you right here. As long as that magnet's on, they're stuck. They are stuck. When you want to clean it out, all right, it comes with a with a blow off, all right? Comes with a blow off. You put the blow off here, you turn off the circulator so there's no more flow, and just open that thing out and take the magnet off and blow that crap right out. So really, really simple.
Anthony's got a bunch of warnings here about you. I mentioned 40 degree. I said out around 40 degrees. Again, follow your boiler manufacturer's recommendation. That's my get out of jail free card. But Anthony, by the way, I have a boiler out there in my garage, and I'm doing 40 all day long. And I've been doing it for about 14 years. So it works. So.
There you go. Chuck LeMay asked about a 20 degree delta T, and I'm wondering if you're asking about system design, not around the boiler pump sizing, but system in general. 20 degree delta T is kind of an arbitrary number. It's what we've been using, as a standard for basically forever. And it's a good number. There's no science that says 20 is ideal. You can design a system to whatever you want as long as you know what it is, right? But you can't do something like say, well, all right, I'll design to a delta T of 100, and that means I can heat this house with like a third of a gallon of water. Now you're getting ridiculous. You don't have enough, flow, laminar flow, that kind of thing for heat transfer. So within reason, all right. Typically, like European style heating systems, for all their drawbacks, are designed around a 40 degree delta T, which is actually about a 20 degree centigrade or Celsius or whatever you want to call it. And they're just, they're at a 40 degree delta T, your flow rate goes way the heck down. Now, the reason they design around a 40 degree delta T to keep the flow rate down is because they use itty bitty pipe over there, man. They use really small, they started really with 14 millimeter Pecks, which is teeny. It's around 3/8. It's a little less than ½ inch. And they would do supply and return, home run supply and returns to different radiators, because when retrofitting those old European homes back in the 60s, it was the easiest way to do it. Okay, it was the easiest thing for them to do would be 2 small pieces of Pecks, home run to this room, home run to that room, home run to that room, home run to that room, all coming back to a central manifold. If they designed around a 20 degree delta T, the flow rate to each radiator would have been high, and through that small of pipe, they would have had to airlift a pump to the job. All right, you would needed a ridiculously high head pump. By designing around a 40 degree delta T and using panel radiators, which lend themselves to a wider delta T, now your flow rates are down, are small, but the head is still relatively high. That's why one of the things when we talk about pump curves, we talked about steep curves and flat curves earlier today. flat curve pumps in the pump manufacturing world, flat curve pumps are considered, it's called an American style curve, where steep curve pumps are considered a European style of curve, simply because traditional use. European systems are low flow, high head because they use the little pipe. All right. They still keep despite the 40-degree delta T, the head tends to be a little bit higher. So they really need a steeper curve pump. Here in the US, back in the late 50s, our 40s and 50s, when we had our building boom, we were putting in hydronic systems into these houses as they were being built. They were big houses, but we were putting the pipe in as the house was being built. We could use bigger pipe. And designing around a 20-degree delta T gave us a high flow rate, but a relatively speaking lower head. And we were able to use flatter curve pumps. We developed flat curve pumps for the applications we used here. All right. They developed steep curve pumps in Europe for the applications they have here. I had a guy once tell me, oh, steep curve pumps, they're hydraulically more efficient. No, not really. They made it. Thank you, Dave. They picked up on it. Yeah. Dave's wearing an ascot. He'll take anything I hand him, I'll tell you.
Well, one thing, speaking of that, that 1-inch I shouldn't say it, Pecks aluminum Pecks product is out there. They make real good travel bongs, you know. So you guys remember that back in the day, I tell you.
Back in the day. There you go.
Back in the day.
Oh God, this is default. Yeah, hey, this is Takeo After Dark, people. You signed up for this, all right?
That's right. And they're
Nobody
still
held
here.
a gun to your head and said, "Come to this show." Okay, that's very good. That's very good. Okay, what other questions do we have here, Jimmy DePalma?
I'm gonna extend on the delta T thing there too. And if you were to extend the delta T, so let's say in a baseboard system in a house, the trick or the worries that you have to get into there is the last couple of radiators on the zone.
Sure.
Because now you have to size that based on a lower temperature. So you're going to need more in there. And there's a lot of homes out there now that people already experienced that with. And, my experience has happened over the last couple of years in doing training classes is if people come up to me and they say, I walked into a house, it's a 30-year-old system. Nothing's changed in the last 30 years. But now all of a sudden they're saying it's not working in a couple of rooms. And the question you have to really stop and think about, well, what's changed? Is there new carpet installed in the house? Nope. Are the heat exchangers all full of dog hair and cat hair? Nope. The big change was the homeowners. So there were a couple of rooms that might have been cold in the past that the homeowners just lived with, but today new homeowners come in, their expectation level is a little bit higher. Hey, those are the kids' rooms. We need to be concerned. We can't have a couple of degrees colder over there. So that's also when we have to need to really start designing and taking a look at some of the lengths that we have installed on the radiation and the delta T that happens. We weren't looking at it when it was first installed, and because, hey, we were running boilers at 210 degrees. Now it's $180 instead. So other things to look at.
There you go. Very good. Hey, this is a question. I'd love to hear what you guys have to say about it, because I know how I feel about it. What about changing a gravity system and adding a pump? What have you guys done with something like this? What's your experience? I'm curious.
I don't have any experience. No.
Oh, well, being out west, you wouldn't. Would you, Dave?
Well, no. There are some old gravity systems in Salt Lake City. I just personally have never been involved with it. Growing up in Alaska and stuff, it just wasn't a deal. So I can't speak to that. I'll let somebody else do it.
Dave, how about you? What's your experience?
Not a lot here on the island where I am, on the east end of the island, that I really got to experience a lot. The conversations that I've had, big in G100, 35 gallons a minute, is the job that it did.
Yeah, so in that case, you do have to move volume because of there's a lot of volume in that system. You got to move volume, but you'd have very little head loss. You have very, very little head loss. All right. Anthony's had some experience. Anthony, can you type in something for us about your experience? That would be helpful, because what you've done with this system is you've taken what amounts to a continuous circulation system, and the expectations with that, a gentle continuous circulation system, that's probably was a little more highly engineered than most systems that are put in today. And you're basically saying, you're not going to work like that anymore. Sorry, you're not working like that anymore. We're going to put you on a thermostat. This pump's going to run on and off in the name of efficiency. So you've basically forced this system to run counter to its nature. So there's always, it's never going to come, in my opinion, they very rarely come out perfect. All right, very rarely come out perfect. But what I've seen is it's got to be a high flow, low head pump, because you got a lot of water you got to move. There you go. All right.
But you don't want to move it too much, too fast, because it was gravity. It was a slow moving system too. So most of my experience with it, where they left the radiation installed, is they went to a manifold style system and went with Pecks,
and
Pecksed out to each radiator. So then it was an easier controlled system rather than just going hog wild as it was before. And then we put actuators on and being able to control the flow out there. So that's about the extent of my experience on them.
Yeah, and that changes the nature of the system too. I mean, you basically completely altered the nature of the system, which you may very well have to do at that point. Yeah. Jordan asked, did we reach our goal of people? No, we wanted 300 of you, man. We were up, I think, close to 200. Tell all your friends, I want 300 people sitting in class next Wednesday. That's what I'm after. I want 300 of you. All right, so
our bonuses depend on it.
No, your bonuses depend on mine. I'm the boss. Your bonuses depend upon it.
Okay.
So someone had a comment about bosses a little earlier, and I think he was probably right. You guys tell all your friends, I want to break the internet, because the internet was made for nights like this. That's my new catchphrase for this. The internet was made for nights like Takeo after dark. And I hope you guys have had fun. It's been fun for us, obviously, but I hope it's been good for you guys as well. And again, we'll stay on as 114 of you still on, man. We'll stay on as long as you guys want and as long as you guys have questions. So let's take a look. What else do we have here? I've seen the problem with those converted with the B&G is they move too much water. Heat transfer wasn't great. Very little delta T in my experience. Yeah, you're changing the whole dynamic of the system. Once you put a pump on a gravity system, it's just not going to be like it was. So it is what it is, I guess. It is what it is. Send out the link for us to pass on for next week's class. Todd, great question. And you know what we're going to do, Todd? When you get your follow-up email tomorrow, okay, you'll get a follow-up email tomorrow, and it'll have a link to the Mechanical Hub YouTube channel to watch the recording. It'll also have your registration link for next week, and you can send that off to anybody you want, man. Anybody you work with, anybody who works with you, just send it. Feel free to pass that along to anybody in the business. We'd absolutely love for you to do that. That would be awesome. So yeah, guys, make sure you pay attention. Look for that follow-up email, and we'll make sure that that'll have your registration link for next week. All right,
sometimes this is kind of a give and take, right? We get stuff from you guys, you get some stuff from us. We make it fair. I'd like to throw out a pop quiz, maybe not a quiz, maybe something to get us an answer next Wednesday. But it's a head scratcher, so I don't want anybody guessing. And in fact, I want you to send it to me, RICMAYMOUSE at Takeo. You knew I was going to say that. Anyway, RICMAY at TakeoComfort.com.
Why? Because we like you.
Yes. Now, what I'd like to know is, we spend a lot of time out west talking about what mode of operation should we run these new ECMs. It's actually a pretty hot topic, but there's one out there that is somewhat of a head scratcher. So put your pencil to it and send me the correct mode of operation. And really, there's only 3 out there, even if it's auto or not. I got variable fixed proportion, I've got constant pressure, or I've got fixed speed. And then you have variables of that. But what I want to know, if I have an old diverter T, without using any names, whatever, Taco's got them, B&G's got them, other people have them. If I have one of those old systems and I'm upgrading and I'm putting an ECM on there, high efficiency circulator, what's the right mode to use on that type of systems? Let's go ahead and re-describe it. It's a diverter T. Let's say it's got zone valves up in the baseboard, okay? And remember, it comes back down into the same run. What's the proper mode of operation? Again, no guessing, send me your calculations.
Interesting, interesting. All right. Very good. All right, cool. Let's see, Bob X says, I have cast iron radiators and there was a Weil McLean oil boiler in with a Taco 110 on the return side and it worked okay. Then I installed a condensing boiler, piped primary, secondary, and piping it this way, all the radiators heated up evenly. Okay, so that works out pretty good. All righty. Jim Hillpiper wants to go through that scale 5 thing real quick one more time. Okay, Jim. Here we go. Let's see, I get this right now. You'll see the line up on the top there, where it says feet ahead, and it's CV. All right, it's a static number. You line that CV line up to the CV rating of the valve or piping component. All right. In this example, I'm using a valve with a CV of 5, so I line up the CV line with 5. What that means is at 5 gallons a minute through that valve, I get 1 psi of pressure drop or 2.31 feet ahead. If you look real close, up top, you see that CV line is right at 2.31 feet ahead. And down below, you'll see that the CV line is at 1 psi. Okay. Now it's real simple. All right. I want to find out what the head loss is at 6 gallons a minute. And I simply, in the white window, just go from 5 to 6, read up, and I'll say, okay, the head loss through that valve at 6 gallons a minute is a little over 3 feet ahead. Looks like about 3¼ feet ahead. I want to find out what it is at 7. I go to 7 and I see that it's at almost 4.5. Jump all the way over to 10 and you'll see that the head loss through the valve is 9 feet ahead. All right. So you line up the CV notch to the CV rating of the valve that you're looking at, and then simply look and see what the actual pressure loss is at the actual flow rate you're running. So for example, if I put a valve with a CV of 5 on this system and the system only had a flow rate of 2, I'd go in the other direction and I'd see the actual head loss appears to be 0.4 feet of head at 2 gallons a minute. So that's kind of how you read that number 5, if that helps, Jim. Again, just a silly, useful piece of equipment or little device. I use this almost every day. All righty, let's see what else we have here.
Somebody's asking from last week about the leak breaker.
Oh yes.
Yeah. So no. If you put it in the vacation, when you leave after 36 hours of no events, then that's what it was. If we turn the thing into closed position, is it going to cycle? And Rick Brendamore did get back to us and say, no, it will not. So Joseph, there's your answer.
If you physically put it in the closed position, it will not cycle.
It won't go through its exercise.
Very good, very good.
Sorry, Joe. I was going to get back to you on that. I forgot.
The question from Antonio: how would you guys determine the actual flow rate or GPM on an existing system? I'd start with, if I really needed to know, I'd start with a heat loss. If I needed to know for the big picture, I'd start with a heat loss. If I was trying to replace a circulator, all right, there's a dead pump and I'm trying to replace a circulator without knowing the calculations, which you're not going to do. Let's face it, you want to replace the pump. You can look at 2 things. The thing I would look at is what type of radiation am I dealing with, and can I get an idea of what what's possibly there, and then I'll look at the pipe size. And I look at the pipe size, and if it's like fin tube baseboard or something, and the pipe size is 3/4 inch copper, I know it's between 20 and 40,000 BTUs. It's between 2 and 4 gallons a minute, because that's all it can be. All right. So I know it's going to be there. And if I went out and measured the radiation and the radiation came back at 30,000 BTUs, I'd be okay going with 3 gallons a minute at that point. You know, so at that point, it's a little bit of interpretation. It's a little bit of, you know, knowing what systems are and what different things tell you. Could it be that they put in 3/4 inch pipe when they needed 1 inch pipe and it was screwed up? Yeah, absolutely. That could happen. You know, that certainly could happen. How do you know that that's going to be a problem? Well, once you put the pump in, if you got a really, really wide delta T and it's not all that cold out, then you know we've got a problem here. So a lot of it is what you know about how systems work. But that would be, you know, short of doing a heat loss calculation, that would be probably, to me, if I'm trying to figure something out, that would be what I would do. Now, we talked about the 0018E a little bit last week and the diagnostics that are available with that pump. When you connect it to an app, you can actually see what's going on inside the pipe. Now, there is an application where you can use the 0018E as a diagnostic. What's going on in here? Where I've got this thing running full bore, where am I? What's the flow rate, etc. So there are ways to use that as well. All righty, very good. Ken Watson, don't sell yourself short, John. You're a tremendous slouch. You were waiting all night for that, weren't you, Ken? Don't you have to go to bed or something? Rest your hair, fella. Rest your hair.
Ask him what his cocktail is. Ken, what are you drinking?
What are you drinking tonight there, Ken? Maybe a Fresca. I don't know, you know.
He's feeling frisky.
Yeah, if I was smart, I would have got a nice bottle of Fresca, but I'm not that smart. I didn't think about that. Yeah, hemlock. No, not hemlock, Anthony. No. Tecotini. There we go. Here's a question from
I like it.
Through your combined experience designing a new system, what would be the most efficient pipe delivery setup? Primary, secondary, home run? The best way to prove it? Ooh. I'm not sure about the best way to prove.
There's the best way to prove it, as long as there's nobody complaining upstairs.
Yeah, there you go. I look at it. I tend to look at things as, okay, what's the challenge ahead of me? What am I looking at in terms of what does the house look like, and what is the most practical way for me to solve this problem? New construction, you know, series loops have been used forever and work very, very well. One of the reasons European systems are the way they are is they started installing residential heating systems, like we said, in very, very old existing structures. A series loop simply wasn't going to happen. You couldn't do it. And my phone just went off. I said series loop, and Siri thought I was talking to her. Siri, quiet. So they did home run systems simply because it was the most practical and, let's just say it, easiest way to do that without performing major surgery on the structure. And it worked fine. You know, trying to do something else, could a piping system have made it slightly more efficient? At what cost and to what degree of benefit? I don't know that you could figure that part out. At that point, any piping system you think about has to be doable for the house, for the building or the house that you're looking at. That's my take on it. I don't know if you guys have different ideas. Please know that.
Well,
please know that I select your bonuses. So if you want to,
I won't.
Yes, John. Great idea. Yes.
Yeah, you're the
sure,
best.
yes, sir.
Yes.
Let me pour another drink.
I'm looking at the question, and it says it's a new system. So let me throw something at Jordan. What if we did things a little different? Now, I have to give credit where credit's due. I first heard this from Robert Bean, and some of you folks know who he is. But we all grew up, I mean, us older folks anyway, grew up thinking that we'd just put some pieces and parts together, and we'd put some heat emitters, and we'd run an appropriate size pipe out to it, and we do this and that, and then we go and say, okay, what does the pump need to be to take care of that system I just built? Well, I mean, we've all done that. I'll raise my hand. But what if we said, I'm going to size all my components based on the usage of a little tiny circulator that I know will do the job as long as I design the system to do that for me. So what we're doing is we're not letting the tail wag the dog, right? What we're doing is we're saying, I can design my system, kind of like John was bringing up, what if I split that zone? That drops my head more than in half. That potentially can get me into a smaller circulator. So, Jordan, there's a lot that goes with your question, and we could go on and on, but I want you to just set that little seed in you. And again, I'll give credit to Robert Bean, because he's the one that had me start thinking about things, and this was years ago, even when I was still doing design systems. And but it's like, let's design this thing around the use of a particular product, not a product, but a size of a product and the wattage of that product, and that's going to get me an overall system efficiency increase. Again, when we let the tail wag the dog, that's where we end up with these Binford 5000s that my buddy John taught me a long time ago. I mean, that's a ridiculously big pump, and everybody's using them. Taco, as well as Grundfos and Velo's version and everything, and those are crazy circulator sizing. So again, start thinking about designing the system to get the most, well, I don't like to say, I'll say the most efficient overall life expectancy of the system. If I think about that up front, I'll be much better off for that building owner, and I'll do a better job of that design.
That's very smart, because remember, earlier we did say the system will do what the pump says. Even if it's a variable speed pump, the system's going to do what the pump says. So that's an interesting design theory. That's very well stated. If you start with the pump and size the system, because you've got a blank page, right, Jordan?
Right.
You got a blank page here, man. Design the system, the delivery, and everything else to fit the pump you would like to use. Now you're there. Okay, I got it. That's really smart. That's really smart. You get a bonus.
It's just putting the different parts and pieces together to fit the project too. So, I mean, how you're piping it is going to, depend upon the boiler. You got a cast iron boiler. All right, we're doing supply return. You know, if you're doing radiant floors with a cast iron boiler, then we're doing primary, secondary. So there's a lot of it depends that will also come into play there on how you're heating the house, and then what the heat equipment's going to be in the end too. So when I recently did my house here, I gutted the place to the studs, so I got to start over, and I went to radiant floor setup here. And I then took a look at, all right, well, I've got this boiler in mind. All right, we're just looking at a wall hung condensing, so I know I got primary, secondary there. But I also knew I was using our Delta T pump. And because our Delta T pump was a high head circulator, when I designed my Pecks tubing loop lengths, it was around the pump itself, saying, hey, I got high head with this. I can go longer on my loops and therefore end up with less connections on a manifold. So I knew what was going on with all that stuff in between. So yeah, you get to play around with that design. And yeah, there's a lot of it depends.
All right, there you go. And one thing is you do want to watch out for a minimum 2 feet per second for certain types of pipe. I mean, there's your low limit anyway. So you do need to watch out for that for laminar flow. But yeah, that opens up a lot of interesting things, man. That's an awful lot of interesting things. And Anthony Reichow makes a really good point. There are boilers out there that will tell you the number of run hours and the number of cycles. Right? That'll tell you if you did it right too. Because if you got a certain amount of run hours and a metric crap ton of cycles, we've done something wrong. We've probably we definitely have over pumped, and the boiler might be too big to boot, but we've definitely over pumped. I think, Anthony, you were telling me you had a boiler once where you did some quick math and you found out the average runtime of that boiler over about a year and a half of service was about 13 seconds. I mean, whoa. The boiler the boiler doesn't have time to get efficient. Nobody was cold though, I'll tell you that. Nobody was cold, but that boiler just doesn't have time to get efficient. So that's kind of crazy. All right.
No one ever talks about steady state efficiency anymore either. And
right.
But that's where that comes in.
Yeah, fewer cycles and fewer longer cycles are better than more short ones. Absolutely. Richard McGrath says designing heating systems for buildings instead of designing buildings for people is counterintuitive. Also, Robert Bean, just what Rick just basically say that right, just what. Yes. Okay. I can't read right now. What he said. There you go. You design systems for people too, right? You're not heating up buildings. You're heating up people, and that's another thing I learned from Robert. Very smart guy. Very smart guy. He is my fourth favorite Canadian. I didn't know if you knew that. On all time, he is my fourth favorite Canadian. You want to know who they are?
Go ahead.
Top five?
Go ahead.
Top five? My fifth favorite Canadian. My fifth favorite Canadian of all time. All right, fifth favorite Canadian of all time is Anne Murray. I just thought she had a wonderful voice, Anne Murray.
Alanis Morissette.
Well, that's because I'm old school. Old school.
I'm older than you are.
Yes, remember? But I'm Anne Murray old school. You're Alanis Morissette medium school.
Okay.
All right. This isn't my favorite Canadians. Okay, you do your list. I'll do mine. Robert Bean's number 4. Okay, Robert Bean is number 4. Neil Young is number 3. All right. Number 2, your friend and mine, Red Green.
Okay.
And number 1, the greatest hockey player who ever laced them up. Number 4, Bobby Orr, my all-time favorite Canadian. That man has brought more joy to my life than any other Canadian ever, including you, James J. House, when you almost damn near tried to kill me in Parry Sound, and I haven't forgotten that. All righty then.
I thought you might mention one of our Canadian brethren.
Mike Miller.
And
Sean Giberson.
Sean Giberson.
Well, Sean's in the second 10. Sean is in the teens. Is in the teens. Mike Miller fluctuates, I mean, he fluctuates, but he's kind of in the William Shatner area for me. William Shatner's 10, 11 in terms of all-time favorite Canadians. That's where Mike Miller is.
Okay.
No Jim Garrett. I'm talking about the top 5 here, man. The top 5. It's hard to crack the top 5.
Yeah, you got names like that in there. Yeah, it is a little tough. Yeah.
Yeah. Well, Sean's going to beat Bobby Orr? I don't think so. All right.
I think everybody's tied for 6th. How's that?
Yeah. The rest of the country is tied for 6th. There you go. Oh yeah.
I did see a good statement also.
After dark takes that serious turn to the left. Okay.
Yeah, it's Takeo getting darker.
All right, we still got 77 people out there listening to the Three Stooges here.
That's right. Jordan actually got another question or statement there. More of a question. Best way to get into the hydronic design industry.
Who's a good person to answer that is Richard McGrath.
Rich McGrath and also our other friend Anthony, our 2 Anthonys down in PA.
The 2 Anthonys down in PA. Yeah, Richard McGrath he's still on here with us. He is takes hydronic heating system design to parts unknown. I mean, he's the George Carlin, and he looks a little bit like George. He's the George Carlin of hydronic design. He looks at things and says, "What the hell is this? What the hell are we doing?" I mean, he looks at hydronics the way George Carlin looked at life, which was to question everything and to call BS where he sees it. And I got so much respect for that. But here's a guy who's taken hydronic system design to just no constraints. It's like, no, why do I have to do it this way? Why can't I do it this way? Let me see if it works. If it doesn't work, I won't do it. But if I can prove that it works, then I'm gonna do it. And just very innovative thinker, and those are the people to talk to. I would recommend folks like that, and see what they have to say about how they evolved from, many of them were like we were, guys working with tools, mechanics and stuff like that, the service guys, the workers, and became a thinker as well as a worker to think about how to do these things and design systems. And that's an interesting jump, an interesting leap that can be made. But guys like Richard and some of the other guys we talked to are really, really interesting. Very good.
I would also add to that, locally, as in understand and get the whole business model that we have. As in, we have the rep agencies that are local to your area. These guys are there to help you. So take advantage and find that guy. And also your wholesaler. And if you have several wholesalers, find that guy that's going to go out the extra way for you to so to speak, work with you. And there's so many avenues to follow. Please take advantage of them. For example, what we've done at Takeo and called Takeo University, Flow Pro University, our online e-learning classes outside of what we have here. Now you can learn on your own times too. So, but take advantage of finding that mentor in the industry too. And there'll be probably guys right next to you that you just don't even know are there. So take advantage of that, definitely.
Yeah, guys like in Pennsylvania, you get guys like Anthony Ryko, who works for FW Web now, and they're great hydronics minds out there. You just got to seek them out. And I'll tell you what, Jordan, in your chat function, if you look, you might be able to see who's there if Richard's still on there or Anthony. Talk to them directly in the chat function of this thing, and then you could press private information there. I don't feel comfortable doing that, but that would be something I'd think about doing there. Just in your chat function, see if you can locate them. Interesting question from Stanley Barge. He's about to take a class from John Sigenthaler on hydronics piping. Do you think that would be a good class to attend, or do you recommend another training course? John teaches fantastic courses, absolutely fantastic courses. 2 thumbs up here. Do understand that there's no such thing, and I'm not knocking John, because John's way smarter than I am. I'll tell you that. But there are very few independent voices in this industry, to the point where I'd say none. Everybody's affiliated with a manufacturer of some sort, whether it's on a consultant basis or like us, we're employees. Okay, we work for Takeo. Okay, and we're upfront about that. So you're always going to get an angle. Everybody's got an angle. Okay, John, three or four different manufacturers, and that he's on. He's been on contract with us too. So just understand that there are no independent voices out there. That's not to say that John's class wouldn't be very, very useful. It very much would be very useful, because I've gone to his classes, and you got to work at it, but there's a lot of good stuff to be learned there. Absolutely. All righty then.
Always take every training class that you go to with what you want to get out of it. That's the most important thing about it. So when you go to a training class, have an agenda before you get there. What do you want to get out of that training class? That's the important part out of it. And as John was talking about before, if you're gonna call bunk on something, call bunk. All right, and make your own decisions on what the guy in the front of the room is saying about it. So all we have is the stuff between our heads to share back out to you guys and our experiences, but everybody has their own too, and you need to interpret that to what works for you and your business too at the same time.
Very good. Very good. Richard has given me permission to share his email address. So it's DM McGrath. So DMCGRATH 40, DM McGrath 40 at Comcast.net. Comcast.net.
It's about to blow up now. And Anthony also wanted to share away his phone number too. So Anthony Rykow works with FW Web. His phone number 267-806-2800. Give it away.
Give it away. Give it away. So there you go. There you go. All righty. Very good, guys. Very good. Very good. Let's see. I want to know more on iValves next week. We can talk a little bit about iValves. Talk about an underappreciated product.
I love that thing.
The iValve, a motorized 3- or 4-way mixing valve with an outdoor reset control built into the motor that runs on 24 volts. I mean, talk about a valve that should have been huge. All right, should have been huge and still can be. Guys, just because you're using a ModCon boiler doesn't mean you shouldn't mix and reset off of the reset. I think there's tremendous benefits to be had to multi-temperature systems with low temperature boilers. and resetting off the reset. So you're sending even lower water temperatures back to the boiler. You know, they're not going to fight with each other. It's just the boiler's going to reset on its curve. These other two things are going to reset based on what those specific things need. And man, oh man, that is just huge. The potential on those things. And I just never really understood why they didn't sell more. You know, why it just was such a brilliant, it is still such a brilliant product. So
every time I talk about that in a training class, I got guys that come up to me and ask me when it's coming out.
You tell them 2003?
Like, 15 years ago, man. It came out a long time ago. I think why a lot of people don't know about it is back at that time is the advent of the ModCon boiler.
Right.
So all of a sudden it was like, all right, we don't need to mix anymore. And what everybody did know about mixing was coming out of Techmar, doing some great stuff on their control platforms, you know, with variable speed injection mixing and also on the mixing valves side of things too, that it just got lost in the mix. So, well, we just like to make stuff and not tell anybody about it.
Yeah, there you go. Well, what we'll do is we'll do a session maybe next week, maybe the week after, just on the eye valve and sizing it, because sizing it is kind of is important too. You don't want them too big. You know, you better to go a little small than a little big on those things and deal with the additional pressure drop. So we'll discuss that. Okay. How do you feel about the Webstone Purge T? I feel very warmly and strongly about it, Mike Flynn. I love it. I think it's a great piece of equipment, man. It's a great piece of equipment.
I got a couple here in my house. I love using that thing.
There you go. There you go. Okay, let's see. It takes 1 month to receive, you guys. Must be making these eye valves to order. 1 month to receive, you
Talking
guys.
about ship times, you know, being out of product and having to wait for it. So who knows? We don't work at the,
It depends on, is Sean McGovern. Sometimes reps have them in stock, sometimes they don't. If they don't have them in stock, a lot of times they will wait till they got a nice big order before they put in an order. So it's not that we don't have them, it's that they don't have them and they're not putting in their order for a little bit. If they want to get the best shipping and not have to whack you for it, you know, that kind of thing. You know, so that might be why you know, your specific situation, I couldn't really comment on. Richard McGrath says try supplyhouse.com. Hey, this online thing is just, I was reading an article today, not to get off topic, but I was reading something online today that said department stores are going, there's a major bankruptcy is going to happen within the next several months for department store chains, including Nordstrom's, you know, because they were struggling anyway, throw in, you know, nobody's going into stores for 2 freaking months now. What are you going to do? You can't do that. So they're not only are they not they're not putting in their order. They're not selling what they have now. They're not putting in their orders for the stuff they want to have for the holidays. So it's a trickle down effect. It's the world in which we live now, I guess. So I don't know what got me off on that tangent other than everybody's buying online. That's what got me there. Yes. Supplyhouse.com. Everybody's buying there. See, we'll get there. I take the detours off of the information superhighway every once in a while, but we'll get back there. So yes, it has to do with online shopping, where I happen to get my Property of Bushwood shirt and my Bushwood Country Club caddy cap. And where Dave got that ascot, I don't even want to know what website you got that off of, because I don't want to know about your online habits.
I'm having fun, man. I'm having fun and feeling good. That's all that matters. Yep.
I like Richard's comment here. It's the end of the world and we know it, and I feel fine. A little REM. There you go. And Anthony, yes, I understand. Yes, not all of us. Sorry, not all of us. All righty, guys. Let's say we can kibitz for a little while longer, or if you guys want any questions. I mean, like I said, we all three of us talk for a living, so we can talk as long as you want. Here's one.
Hey,
Go ahead.
No, I was just going to say maybe we forgot something up higher if somebody wants to send it back, or if we missed your question, send it again.
There you go. Here you go. Here's one from Colin. As Dan's dad always said, people will still need heat, especially when it's cold. Yes, that is why we are still in business. Absolutely. And does Dave have a members only jacket too? Oh,
I
yes.
don't. I do not. I do not. But yeah, the high school.
No club would have him as a
picture.
member. No club would have him as a member, Mike. That's why he doesn't have a members only jacket. That's all right. I wouldn't want to belong to a club that would have someone like me as a member either. All righty. Well, guys,
they let just Dave in though.
They let just Dave in. Yeah, just Dave.
That's right, Mike.
Just Dave. Okay, there's my team. Just Dave and the Lorax.
Here's one, Bob Farrow. He's wanting to know if it'd be a good idea to update a traditional 007 F5 to a 0018E. I would say absolutely, if you get the opportunity. I mean, if somebody says, I don't want to update my system, that'd be a great pump. I have one out as my system pump right now, but I'm about to put one of those in its place. So that's another story.
That's another story.
Now Rick is doing that only because he knows people where he can get pumps at a relatively low price. You know, if everything is cool in your house, Bob, and nothing to worry about, then why mess with it? You know, if it's been there for, since 04, I mean, you look at around an 18-year, 20-year lifespan. It all depends on cycle count that you have out of a circulator. If it's still running, I'd leave it. If you're looking at, if it's, when it goes, then I would consider doing it. So then you've got the choice to really see what you can get out of it. Definitely. So, yeah. If you want to put it on the return side or the supply side, that depends how much work you want to do.
I mean, if your pump has been on the supply side or been on the return side forever.
Yeah, exactly. Leave it there. I wouldn't mess with it. Yep. You make that 18E operate like close to what you had before as your 7E, then you go. If you're out of whiskey. So if you have that down by the boiler, then time to go take a look at it. I'm just seeing the questions pop up from Bob. Good to see you, brother.
You're looking for efficiency. Well, you will get some electrical efficiency. I mean, the 007 doesn't use a lot of electricity. Let's be serious. It's a 125th horsepower, 85 watt pump, that runs maybe 2,500 hours a year. All right. If it costs you $30 a year to run that, okay, you could knock that down by a good margin by putting in a 0018E. Maybe you cut that down to about $8 or $10 a year. Okay, that's okay. That's fine. You can certainly do that. If you want to make the system operate more efficiently and eliminate white space between your requirement and the pump curve, now you got something you can do here with the 0018E. You have the ability to run it in a constant pressure mode or an infinitely adjustable fixed speed mode, all the way from 5 watts to 44 watts or so, anywhere in the middle. So, and you have the capability of verifying it through the app. So you can make that system work a little bit more efficient.
Well, there's another idea. He's looking to save some fuel. He's not worried about the electrical. So 2218 may be a better choice in his application. So we haven't gotten to that circulator yet. All right. So that'll be another conversation to come on back. We're going to keep you hanging, man, just like most of those TV shows right at the last second. We're going to show you some really cool stuff that's going to happen next week. But the VT2218, that might be the circ you want to look into.
Hey, there you go. And there's your cliffhanger. There's your cliffhanger. All righty.
Like Oak Island. Yes, sir. That's right. That's right. Yep.
Okay. Well, we've been on this for 2 hours and 20 minutes, gang. This is just great. We'll stay on and talk as long as you want. I'm running out of battery, and my thing has decided to not charge again. So I may have to take my leave, but we'll.
I still got a whole bottle to go, man. So I'm good. I don't have to work tomorrow.
Hang on. All righty then. Okay, there we go. Now we're charging. Very good, very good. I got a wonky charger on my thing. I don't know. Jason Mangos is on the line. Hey, Jason, how are you doing? How's life treating you? All right, Jason Mangos, one of the industry's bright youngish people. I don't know. Is Jason still considered young in our industry, Dave? I don't know. You don't know Jason, Rick, but Jason's a really sharp boiler dude from Pennsylvania. And I don't know, would you consider Jason young? He's younger than me, but I don't know what that means.
Yeah. Well, he's younger than me then too. Yeah. So he's in his early 40s.
So he's 43. That makes him, Wheel says, no, he's not young. Yeah, that makes him a youngster. If he's half my age. No, he's not half my age. I'm not 83, Wheel, so I'm not 83. I think I'm younger than you. I think I'm younger than you. Now you want, okay, off topic, but there's still 50 of you out there and nobody's asking questions, so here we go. Steve Whelan went to high school with my landlady who lives downstairs. We found that out by both of us happened to comment on one of her Facebook posts one day. And he wondered, how do you know Bonnie? I said, well, she's my landlady. She lives downstairs. I live upstairs. And they went to high school together. But I'll tell you what, Steve, I asked her about you. She doesn't remember you. She doesn't remember you. How about that? She doesn't remember you. Jim Hillpiper, tell you what, I'm going to do something here for you. I just want to give you let me type in my email address for you, Jim. All right.
And the chat section's over on the right-hand side. It's in your toolbar. You should see a chat area, I believe. Actually, maybe they're not available.
I think everybody's doing the questions, though. I don't.
Yeah, I think chat is available to the organizers.
Available, but yeah, I'm just looking at questions bar. So.
All right. Question popped in from Antonio. Do you guys prefer to see expansion tanks on the return or the supply? Now, so Antonio, that's what I was talking about here before with this display that I have, showing about pumping away from the expansion tank or into the expansion tank, was basically the supply return. Supply return really doesn't matter about the boiler. It matters where the expansion tank is in the system itself. When the pump is on the return side of the boiler, yeah, it just so happens a lot of times that expansion tank's going to be on, you're pumping into that thing. So that's what I was talking about with this display before. It has nothing to do with the boiler. It's got everything to do with the expansion tank. So hopefully that answers your question. If not, take a look at last week. We went through that in the presentation. That's on mechanicalhub.com's YouTube page. You can take a look and review that again. Also on our page on the Flow Pro University, we have that in there too. So there's a lot of places that you can go back and review. Basically, it was about 20 minutes or so last week that we had done on the pumping away section. Or grab yourself, get Dan Holohan's book, Pumping Away. That'll tell you a lot about it. But make sure you read it to the end.
Yes,
don't stop and stay and in the middle of it and say, oh, I'll pump away always. Right. Get to the end of the book too. Yes, definitely.
Right. There's something from Sean McGovern. You guys normally run the eye valves in the factory then? Supplyhouse.com, local supplier says eye valves are always on special order. That means they may not stock them. That's probably where that means. They probably don't stock them. But we have runs of them. I don't know where we are in terms of stock, but that's not something we generally run out of. It's going to depend on whether your wholesaler has it and whether their rep has it, because the rep is the local stocking agent. So again, you might have to. It may not mean that we don't have it. It just may mean that they don't have it, and they'll have to order it. It's not that they get. It's not like the wholesaler sends an order to us. It actually goes from the wholesaler to the rep, and if the rep has it, he can send it to the wholesaler. If the rep doesn't have it, then he has to get it from us, and it depends on when he gets it from us. Right. And when he puts an order in to us for it, and does he want to buy just one, or does he want it to be part of a stocking order? There's a lot involved there. That's why again the online suppliers may be able to help you.
And the way that we do our manufacturing up in Rhode Island is that we don't build to stock. So we don't have a huge warehouse. We have 64 smaller warehouses set up throughout the country.
Right, there you go.
So depending upon what the rep has, and they order from us. So we don't have a lot just sitting around at Takeo saying, all right, we'll just send them out whenever we want to. We build to orders based upon our rep agencies throughout the country itself. So so that may be why you run into the lag of not always getting it in special order. So it's just based on area. And like we said with iValves, it's one of those things that nobody knows we make. We wish everybody did know about it. So we try to get to training classes as much as possible and talk about it, but that's always a challenge.
Yep, there you go. There you go. Can you talk about injection pumps and how to select? Well, small is good. There's a lot of math involved there, Kevin. But again, it's all GPM equals BTUH divided by delta T times 500. If you're trying to inject, say 50,000, 20,000 BTUs in a variable speed injection mixing outdoor reset kind of thing, the delta T is the difference between the water coming from the boiler, the primary water temperature, and the return water from your lower temperature system. So if it's 180 from the boiler and you're sending back 100-degree water, you're dealing with an 80-degree delta T. So now it's GPM equals BTUH divided by 80 times 500, or 40,000. So let's say it's 8. I'm trying to inject 40,000 BTUs, all right, from one side to the other, and I've got an 80-degree delta T. Okay, 40,000, that's a gallon a minute. All right, that's one. I need a pump that'll do 1 gallon a minute, and the head loss is next to nothing, depending upon how long the injection legs are. So 1 gallon a minute, you're talking half-inch pipe, and you're going to need some kind of a balancing valve on it to make sure the pump works on its pump curve somewhat judiciously. So yeah, man, that's it. It's not a whole lot more difficult than that. That's the arithmetic, but it's GPM equals BTUH divided by delta T times 500. In this case, it's the delta T between the water going from the boiler or from the high temperature to the into the lower temperature, and the water coming from the low temperature back in. And Dave has quickly drawn a diagram.
It's the magic of delta T. So if you look in the middle there, that injection pump there, that injection pump sees 180 degrees going out and coming back at 100. Let's say you had that tied into a radiant floor system at a 20-degree delta. That's where injection really takes into play, that magic of delta T right there. So, it was beautiful in the days when we had cast iron boilers, high temperature, low temperature radiant. It was a wonderful thing. Now we look at different types of boilers, mod cons more often, low temp boilers, and then where we look at more I valves or mixing valves doing a better job at that application.
Yeah, when the difference in temperature between the boiler water and the return water starts to get smaller, then you need a bigger pump, and then it becomes kind of unnecessary. That's when, as Wheels is saying here, an I valve actually makes a much better choice. In terms of just effectiveness, in terms of simplicity, in terms of piping, it just makes it just a lot more simpler, easier, and more effective. So, alrighty, very good. Last call for questions, because now I'm starting to get sleepy. Okay, 2.5 hours, guys. We've hit a new high, 2.5 hours. And as I said, this is a new record. Our main skill is the ability to talk nonstop and not get tired. All right. Basically, we just sat through a Hollywood epic movie. It's 2.5 hours. That's how long the three of us have been yakking.
And that doesn't count earlier today too for everybody else that we've been doing webinars for.
Oh gosh, yeah. Our
webinars. And for any of you guys that have sat through any of our webinars throughout this entire process, greatly appreciate you guys hanging out with us. So, it's one of those things that, our job is to organize groups of people, and we're not allowed to do that anymore. So, right. I do greatly appreciate a lot of people that have gotten online, and I know a lot of people that are here tonight have been through some of the webinars with me. And possibly with Takeo Tuesdays. I mean, hell, yesterday, 711 people.
711 people on our midday webinar. Yeah.
Wow. I mean, that was just amazing. So, that means a lot of people are home and they want to hang out with us. So it was a good time. So
Yeah.
good. Thank you, everybody. Thank you, everybody, for coming to hear what we've got to talk about too.
Very good. I will definitely echo that. Thank you for the gift of your time. Rick, any parting words for you as well?
Just appreciate it. It's a whole new world for not jumping on an airplane and traveling 40, 45 weeks and sitting behind a computer doing this. Thank you for giving us your time. Appreciate it a bunch. So.
We're going to lose our platinum status on Delta, Rick.
I think they're going to extend it through 2021. So
good for them. They should. It's what else are you going to do? There you go.
And I'm gonna echo what Johnny says. Johnny always, when I do a training class, when John does a training class at the factory, and Johnny wants to stop by and say hi all the time. And actually, Johnny did come and visit tonight. Didn't realize it until he was already gone. So he would probably have loved to talk to everybody here. But Johnny says, thank you for the gift of your time, because that is the one thing that you cannot get back. All right. So we greatly appreciate the gift of your time that you donated to us, that you wanted to hear what we had to say for a couple hours. So, that just makes it all worth it all the time. So
I sincerely hope we made it worth your while. And for you guys to stay on 2.5 hours, you either had absolutely nothing else to do or this was worthwhile. And I'm hopeful that it was worthwhile for you. So thank you all. And we will see you next week on
Takeo After Dark.
After Dark.
Wednesday.
We'll see you all later. Bye-bye.
Peace out. See ya.